Hello there, and welcome to Physics with William, where curiosity gets cozy, the universe lowers its voice a little, and science takes the scenic route towards sleep. Tonight, we're going to sit with a question that sounds simple at first, then quietly becomes one of the strangest questions a person can ask. If time is relative, what time is it for the universe? Not what time is it in London, or Warsaw, or New York, or on the clock beside your bed. Not what time your phone says, or what time the kettle claims it is when it refuses to boil faster. I mean the bigger question, the very large one. The question that looks up from our little human schedules and asks whether the universe itself has a time of day. Does the cosmos have a clock? Is there a universal now, a single grand moment that everything shares, from your pillow to the farthest galaxy? Or is time more local than that? Something measured differently depending on where you are, how fast you move, and how strongly gravity pulls on the place you happen to occupy. Before we wander too far into deep space, let me ask you something much closer to home. What time is it where you are right now? Maybe it is late at night and the room is quiet except for the soft hum of a heater, the faint noise of traffic, or the occasional creak of a building settling into the dark. Maybe it is early morning, and you are listening before the day has properly found its shoes. Maybe you are somewhere between waking and sleeping, which is already a kind of private time zone of its own. And where are you listening from? Somewhere cold, somewhere warm, somewhere rainy, somewhere where the sky is bright even though another part of the world has already turned its face toward night. It is a fitting thing to ask during a journey like this, because every listener arrives here from a different place, under a different sky, with a different clock nearby, and yet somehow we meet in the same small pocket of attention. That is already a clue. Human time is stitched together from agreement. We agree that noon means the sun is high, or at least once meant that before time zones tidied everything up. We agree that a train leaves at a certain hour, even though trains have been known to behave as if they consider time more of a suggestion than an obligation. We agree that birthdays, workdays, appointments, dinners, deadlines, and bedtime all belong to a shared system. It gives our lives order. It lets us coordinate. It keeps society from becoming one long confused picnic where everyone arrives on a different Tuesday. But the universe does not seem especially concerned with our calendars. It does not keep office hours. It does not check the clock before forming a galaxy. Stars are not waiting for the weekend. Black holes do not apologize for running late. On the larger scales, time is not managed by bells, screens, watches, or the quiet panic of realizing you forgot something important 10 minutes after leaving the house. And yet the universe does have a history. It was once hotter, denser, brighter, and far simpler than it is now. It expanded. It cooled. Matter gathered into clouds. Clouds formed stars. Stars made heavier elements. Some stars exploded. Planets formed from the remains. Chemistry grew more complicated. Somewhere, much later, life appeared. And eventually creatures like us began looking back across space and asking what time it is. So even if the universe does not own a wristwatch, it does seem to have an age. Scientists often say the universe is about 13.8 billion years old. That number sounds impressively official, and in many ways it is. It comes from careful measurements of cosmic expansion, ancient light, and the large-scale structure of space. But the moment we remember Einstein, the question becomes less tidy. If time can slow down for fast-moving objects, and if time can slow down near strong gravity, then whose 13.8 billion years are we talking about? Whose clock has been counting? Is that the time experienced by Earth, by distant galaxies, by the light crossing the universe, or by some imaginary observer floating calmly outside everything, which is already suspicious because there may not be an outside everything? This is where the trouble begins, gently, like a cat knocking one small object off a table just to see what happens. In ordinary life, time feels universal. A minute for me seems like a minute for you. If we're sitting in the same room and the clock on the wall moves forward, we can both complain equally about how slowly a meeting is going. But relativity tells us that this agreement is local. It works well when we are close together, moving slowly compared with light, and living in roughly the same gravitational conditions. That is most of daily life. Your kitchen, your street, your favourite chair, your sleepy late-night cup of tea. In that familiar setting, time behaves politely. It arrives in seconds, gathers into minutes, and gives everyone the impression that it is marching at the same pace. But the universe is not a kitchen. It contains galaxies moving away from one another as space expands. It contains stars whipping around galactic centres. It contains planets orbiting stars, moons orbiting planets, and particles moving at speeds that make everyday motion look like a lazy stroll. It contains neutron stars where gravity is so strong that time near the surface runs differently from time farther away. It contains black holes where the difference becomes so extreme that the word now starts to lose its comfortable meaning. Even here on Earth, time is not exactly the same at sea level as it is on a mountain. The difference is tiny, far too small for a person to feel, but it is real. A clock higher up, farther from Earth's centre of gravity, ticks a little differently from a clock lower down. Your head is, in a very small and deeply unhelpful way, aging at a different rate from your feet. This is not useful for avoiding birthdays, but it is useful for understanding that time is not one single thing poured evenly over reality. So when we ask what time it is for the universe, we have to be careful. We may be smuggling in a human habit. We're used to asking for the time because there is usually a clock nearby, and the answer is practical. It tells us whether dinner is ready, whether the shop is open, whether we should be asleep, or whether we have accidentally watched several videos in a row while claiming to be just winding down. But the universe is not located in a single place, where one clock can hang on the wall. There is no central station with a master clock above it. There is no cosmic announcer saying that the next galaxy formation event will arrive at platform 3. Instead, every clock belongs to a path through space and time. Every observer carries their own measure of duration. Every region has its own history shaped by motion, gravity, and the expansion around it. Still, cosmology does something clever. It finds a way to talk about a kind of cosmic time. Not because time is absolute in Newton's old sense, but because the universe on very large scales has a useful pattern. If we zoom out far enough, beyond individual stars, beyond galaxies, beyond clusters of galaxies, the universe looks surprisingly uniform. Not perfectly uniform, of course. There are clumps and voids, bright regions and dark stretches, magnificent structures like glowing threads in a vast web. But averaged over enormous distances, the universe appears broadly the same in every direction. This large-scale smoothness lets scientists define a convenient clock. It is the clock of observers who move along with the overall expansion of the universe, not racing through space in some unusual way, but drifting with the cosmic flow. For such observers, the universe has an age. Their clocks can count from the hot early state to the present cosmic era. This is the time usually meant when scientists say the universe is 13.8 billion years old. That sounds almost like the old universal time has returned, wearing a respectable coat and pretending nothing happened. But it has not. Cosmic time is not the same as saying everyone everywhere shares one exact present moment in a simple absolute way. It is a useful measure built from the large-scale structure of the universe. It works because the universe has a history that can be described statistically, smoothly, and consistently when viewed from far enough away. It is like saying the ocean has a surface level, even though up close there are waves, ripples, foam, tides, and one determined duck. The average description is real and useful, but it does not erase the local details. In the same way, cosmic time gives us a powerful way to describe the age and evolution of the universe, while relativity still tells us that time measured by individual clocks depends on motion and gravity. This is one of the reasons the question is so interesting. It sits at the meeting point between our need for a simple answer and nature's habit of giving us a layered one. On one layer, yes, the universe has an age. We can speak of early times, later times, the first atoms, the first stars, the formation of galaxies, the birth of the solar system, the appearance of life on Earth, and the present era in cosmic history. On another layer, no, there is no single cosmic now that every place must agree on, in the way our intuition expects. Two events separated by great distances may not have a universal order of simultaneity that all observers share. What counts as happening now over there depends on how you're moving here. That is not because reality is vague in a casual sense. It is because the structure of space and time is different from the one our everyday instincts evolved to handle. Our brains are very good at tracking fruit, faces, footsteps, weather, danger, and whether someone has taken the last biscuit. They were not built by evolution to casually picture the relativity of simultaneity across billions of light years. So if this feels strange, that is not a personal failing. It is just your brain being a sensible Earth creature. The word universe also causes mischief. Sometimes we use it to mean everything that exists. Sometimes we mean the observable universe, the region from which light has had time to reach us since the hot early phase. Those are not necessarily the same thing. The observable universe is centered on us only in the sense that any observer has their own observable region centered on them. We are not at the middle of all creation. We are at the middle of what we can see, which is true for everyone, including any patient astronomer in a galaxy far beyond our view. Their observable universe would be centered on them. They would see some regions we cannot see, and miss some regions we can. So even the idea of the universe's time is connected to what can be observed, measured, and compared from within the universe itself. This can make a person feel very small, but it can also be oddly comforting. We do not need to stand outside the cosmos to understand something about it. We cannot step beyond space and time with a clipboard and ask the universe to confirm its date of birth. Yet from inside, from one small planet around one ordinary star, we can measure ancient light, track the expansion of galaxies, study the chemistry of stars, and build a coherent story of cosmic history. That is remarkable. We are like passengers on a ship who cannot leave the ocean, but who can still learn the age of the waves, the direction of the currents, and the shape of distant storms by watching carefully. Science often works like that. It does not require us to be outside nature. It asks us to notice patterns from within it. And perhaps that is why this topic is so well suited to a quiet evening. Time is one of the most ordinary things in our lives, and one of the least ordinary things in physics. We feel it in tired eyes, in meals, in seasons, in the changing light on a wall. We measure it with phones, watches, calendars, and the slightly suspicious confidence of microwave countdowns. But when we follow it outward, past Earth, past the Sun, past the Milky Way, time becomes connected to expansion, gravity, motion, and the origin of everything we can see. The same idea that tells you whether it is time for bed also helps describe the first few moments of the cosmos. That is a wide range for one little word. There is also a gentle human side to the question. Asking what time it is for the universe is really another way of asking where we are in the larger story. Are we early? Are we late? Are we living in the bright middle years, when stars still burn and planets still form and the night sky still has things to show us? The answer seems to be that we live in a universe old enough to have made complexity, but still young enough to be full of light. Many stars have died, but many still shine. Galaxies are mature but not gone. The cosmic background has cooled, but it is still detectable. The universe has expanded enormously, but it has not yet faded into darkness. We arrived at a time when the universe can look back at itself through us, which is a grand sentence, yes, but also a practical one. Our eyes, telescopes, instruments, and mathematics are made of matter that the universe produced over time. When we study time, time has somehow produced the student. Now, before that thought becomes too pleased with itself, let us bring things back to the room you are in. Maybe there is a clock nearby. Maybe you can hear it. Maybe there is no ticking at all, just a glowing number on a screen. That number belongs to your local life. It is useful. It matters. It tells you where you are in the day. But above you, around you, and through you, every atom is part of a much older timing system. Some of the particles in your body have existed in one form or another since the early universe. Some of the heavier elements inside you were made in stars that lived and died before Earth formed. Your body is not just in time. It is made from the results of time passing. Every breath is late in the cosmic day compared with the first light, and early compared with the long future still ahead. That is not a reason to worry. It is just a reminder that the present moment is local, personal, and also connected to an enormous history. If you find this kind of journey soothing, or if it gives your mind something calm and spacious to hold while the day loosens its grip, I would be very grateful if you liked the video, subscribed, or shared this quiet corner of physics with someone who might enjoy drifting through the universe at a gentler pace. It helps this little place reach more curious travellers, more night thinkers, more people who came for a simple answer and stayed, because the universe politely refused to be simple. And if tonight's question keeps you awake for a little while, I do apologise, though only a little. There are worse reasons to be awake than wondering whether the cosmos knows what time it is. So let us begin by setting aside the idea of one perfect master clock for everything. Let us loosen our grip on the familiar notion that now is the same everywhere. The story starts with a change in how science understood time, a change that did not arrive because someone wanted the universe to be strange, but because measurements of light and motion forced the issue. Before we can ask what time it is for the universe, we need to understand why time stopped being absolute in the first place. And that brings us to Einstein, to clocks that disagree without being broken, and to the surprising discovery that time is not simply what the clock says, but what the clock experiences along its path through reality. To see why the universe refuses to keep one simple clock for everyone, it helps to begin with the kind of clock you already know. Not an atomic clock in a laboratory, not a satellite clock circling Earth, not some delicate instrument guarded by scientists in white coats, but an ordinary clock in an ordinary room. Imagine it sitting on a bedside table. It ticks quietly, or perhaps it glows without ticking at all, changing its numbers with silent confidence. In daily life, we trust such clocks completely. If one clock says an hour has passed, we expect every honest clock nearby to agree. If two people leave a room and return later, we expect them to have aged by the same amount, unless one of them has had a very stressful afternoon. Time, in that familiar setting, behaves as if it belongs to everyone equally. It is the shared background of errands, meals, sleep, work, birthdays, and the slightly surprising realization that it is already Thursday. That ordinary trust in time is not foolish. It works extremely well for ordinary life. If you are baking bread, waiting for a bus, meeting a friend, or deciding whether it is too late for another cup of tea, you do not need relativity. You need a clock that behaves itself. The world around us seems to support the old idea that time passes at the same rate for everyone, everywhere. Your watch and the kitchen clock may disagree because one of them has a weak battery, but not because the universe has decided to give them different personal histories. A minute seems to be a minute. An hour seems to be an hour. Time seems like the one thing we can all stand inside together. For a long stretch of scientific history, this was also the serious picture. Isaac Newton described time as absolute, flowing evenly without regard to anything outside itself. In that view, the universe had one great invisible clock. Everything happened against that background. Planets orbited, apples fell, tides rose, pendulums swung, and time moved forward at a constant pace, unaffected by all the motion and matter it was helping us describe. It was a clear and powerful idea. It gave science a stage on which the motions of nature could be calculated with extraordinary success. Newton's time was firm, steady, and dependable. It was the sort of time that would arrive early to an appointment and bring a notebook. Then light caused trouble. Light has a habit of doing that. It looks gentle enough when it comes through a window in the morning, but in physics it has repeatedly behaved like a polite messenger carrying deeply inconvenient news. By the late 19th century, scientists had learned that light was an electromagnetic wave, and they naturally expected it to behave like other waves. Sound waves travel through air. Water waves travel across water. So it seemed reasonable to ask what light waves travelled through. Many scientists imagined a mysterious medium filling space, often called the ether. Earth, moving through this ether as it orbited the sun, should have felt a kind of ether wind. Light moving with that wind should appear to travel differently from light moving against it. Careful experiments looked for this difference, and the difference did not appear. Light seemed to move at the same speed no matter how Earth moved. This was not a small inconvenience that could be tucked away in a drawer and ignored. It was a clue that something basic about time, space and motion was not what people thought. If light always has the same speed for every observer, then some familiar assumptions have to give way. The universe does not let you simply add your speed to the speed of light in the everyday way. You might add the speed of a thrown ball to the speed of a moving train. Light plays by a stricter rule. It keeps its speed, and reality adjusts around that fact. This is where Albert Einstein enters the story. Not as a wizard, not as a lonely genius pulling strange ideas from nowhere, but as a physicist willing to take the behaviour of light seriously. In 1905, while working at the Swiss Patent Office, Einstein published his theory of special relativity. The theory rested on a simple-sounding idea with enormous consequences. The laws of physics are the same for observers moving steadily relative to one another, and the speed of the light in empty space is the same for all of them. Say that slowly enough, and it feels almost harmless. Let it unfold, and it changes time. The key point is that if the speed of light is fixed for everyone, then time cannot be fixed for everyone. Space cannot be fixed for everyone either. Measurements of time and distance have to depend on the motion of the person doing the measuring. This does not mean that time becomes imaginary, or that clocks become unreliable, quite the opposite. Each clock measures its own time properly along its own path. The strange part is that two clocks following different paths through space and time may not agree when they meet again. Neither has to be broken, neither has to be lying. They have simply experienced different amounts of time. A gentle way to picture this is to imagine a clock made of light. It is a thought experiment, not something you need to build on your bedside table, unless your bedside table is unusually well funded. Imagine two mirrors facing each other, with a pulse of light bouncing between them. Each bounce marks a tick. For someone sitting beside the clock, the light moves straight up and down between the mirrors. The ticks are simple. But for someone watching that clock move past at high speed, the light does not only move up and down, it also travels sideways because the whole clock is moving. From that outside point of view, the light follows a longer path between ticks. Yet light must still move at the same speed. If the path is longer and the speed remains the same, the tick must take more time. The moving clock runs slower compared with the observer watching it pass. No formula is needed to feel the force of the idea. A moving clock ticks more slowly relative to a clock at rest with the observer. This is called time dilation. It does not happen because motion damages the clock. It happens because motion changes how time itself is measured between observers. A mechanical watch, a digital clock, a heartbeat, a chemical reaction, a growing hair, a thinking brain, all of these belong to the same timing of the moving system. If you travel fast enough, your whole physical process of aging slows relative to someone who stayed behind. You would not feel slowed down, your thoughts would not seem syrupy, your watch would not look lazy to you. Inside your own motion, everything feels normal. It is only when you compare clocks after different journeys that the disagreement appears. This is one of the most important things to keep calm and clear. Relativity is not saying that time only seems different because of an illusion or bad observation. It is saying that time measured along different paths can actually be different. Your own clock is always normal to you. Other clocks, moving relative to you, may appear to tick differently. When the clocks reunite and compare histories, the difference can be real. Time is not a universal liquid poured evenly into every cup. It is more like a length along a route, and different routes through space and time can have different lengths. The famous example is often called the twin story. Imagine two twins. One remains on Earth, the other travels in a spacecraft at a very high speed, turns around and returns. When they meet again, the travelling twin is younger than the one who stayed home. This can sound like a paradox because each twin might think the other was the one moving, but the journey is not symmetrical. The travelling twin changes direction, accelerates, and follows a different path through space and time. The result is that less time passes for the traveller, not less time according to their feelings while travelling, but less time when their clock and body are compared with the twin on Earth. It is tempting to treat this as science fiction, because the speeds needed for a dramatic effect are far beyond ordinary travel. But the effect itself is real and measured. Particles moving at high speeds live longer than they would if they were at rest. Atomic clocks flown on aircraft have disagreed with clocks left on the ground by tiny amounts, just as relativity predicts. Astronauts experience small differences and elapsed time compared with people on Earth. These differences are far too small to make anyone return from orbit looking noticeably younger, which is a pity for space tourism advertisements, but they are real enough to matter in precision science. Special relativity deals with steady motion, but time has another way of changing its pace. It also depends on gravity. Here Einstein had to go further. After special relativity, he spent years thinking about gravity, acceleration, and the structure of space and time. In 1915, he presented general relativity, a deeper theory in which gravity is not treated as an ordinary pulling force in the old sense. Instead, matter and energy shape space and time, and objects move along paths in that shaped geometry. That sentence can sound grand, but the practical result is wonderfully direct. Gravity affects time. A clock closer to a massive object ticks more slowly than a clock farther away. The stronger the gravity, the slower the clock runs compared with one in weaker gravity. Again, this does not mean the clock feels wrong to itself. If you lived near a strong gravitational field and everything around you shared that same condition, your local time would feel perfectly normal. You would boil an egg, blink, breathe, and complain about slow-loading screens in the usual way. The difference appears when your clock is compared with another clock that spent time farther from the mass. Even Earth creates this effect. A clock at sea level ticks a little more slowly than a clock on a mountain because sea level is deeper in Earth's gravitational field. The difference is tiny, but modern clocks can detect it. A clock in orbit is affected by both motion and gravity. Its speed tends to slow it relative to clocks on Earth, while its greater distance from Earth's gravity tends to make it tick faster. Both effects must be accounted for. This is not philosophical decoration. It is engineering necessity. Satellite navigation depends on clocks that are corrected for relativity. Without those corrections, the positions reported by navigation systems would drift and become badly wrong. Every time a phone finds a route through a city, it is quietly relying on Einstein's strange clockwork. That is a useful moment to pause, because it shows how far relativity has travelled from being a wild idea about the nature of reality. It is not only about black holes, spaceships, or thought experiments. It is built into technologies that many people use without noticing. Relativity is not waiting at the edge of the universe. It is present in the timing signals above your head, in satellites moving through weaker gravity, in systems that have to understand that time does not pass at exactly the same rate everywhere. The universe is subtle, but it leaves receipts. So why does standing in a different place change time? The phrase "where you stand" can mean two related things. It can mean your state of motion, because an observer moving relative to another measures time differently. It can also mean your location in the gravitational field, because a clock closer to mass ticks at a different rate from one farther away. In both cases, Time is not separate from the physical situation of the observer. There is no clock floating above all conditions, untouched by motion, gravity, or history. Every real clock is somewhere. Every real clock moves somehow. Every real clock has a path. This path is the heart of the matter. In relativity, a clock does not simply sit inside a universal time. It traces a route through space and time, and the amount of time it records depends on that route. If two clocks begin together and later reunite, their readings can differ if they have travelled differently. One may have moved faster, one may have spent time in stronger gravity, one may have taken a path through reality that simply contains less elapsed time. It is not that one clock lost time, it experienced less time. That phrase can feel uncomfortable because it pushes against daily intuition. We're used to thinking of time as something outside us while we move through it. Relativity suggests a more intimate picture. Time is something each object carries along its own world line, its own history. A person sitting quietly in a chair, a satellite orbiting Earth, a star near the centre of a galaxy, a particle racing through the upper atmosphere, all have their own measures of time. They are not floating in one universal current in exactly the same way. They are each tracing a different line through the four-dimensional structure of reality. This does not mean that anything goes. Relativity is not chaos. It's not saying everyone gets to choose their own time like choosing a favourite biscuit. The differences follow strict rules, and those rules have been tested again and again. If you know how something moves and what gravitational field it experiences, you can predict how its clock will compare with another clock. The universe is not vague. It is precise in a way that is stranger than common sense, but more reliable than common sense when measurements become exact. One reason common sense struggles here is that human bodies live in a very narrow range of speeds and gravitational conditions. We do not run near the speed of light. We do not spend our afternoons beside neutron stars. We do not pop over to the edge of a black hole to compare watches, which is probably wise, since black holes are not known for their hospitality. On Earth, moving at walking, driving, or even airplane speeds, relativistic effects are usually tiny. Our brains evolved in a world where Newton's time is an excellent approximation, so the older picture feels natural not because it is fundamentally true, but because it is good enough for creatures who need to find food, avoid danger, cooperate, sleep, and occasionally remember where they put their keys. Einstein did not make everyday time useless. He explained why everyday time works locally and why it fails when pushed too far. Near Earth, at low speeds, clocks mostly agree well enough for normal life. That is why you can meet someone for lunch without calculating the curvature of space and time around the restaurant. But the agreement is not absolute. It is a practical harmony produced by similar motion and similar gravity. Move faster, climb higher, orbit Earth, approach a dense star, and the differences grow. The deeper truth was always there, hidden beneath the smooth surface of ordinary experience. This deeper truth also changes how we think about the universe as a whole. If time depends on the path of each clock, then asking what time it is everywhere becomes difficult. There may be many clocks, many paths, many local histories. A galaxy far away is not simply sharing our present in the way another person shares a room. The light we see from it may have travelled for millions or billions of years. We see it as it was when that light began its journey, not as it is at this instant according to some universal clock. And because simultaneity itself depends on motion, even the phrase "at this instant over there" becomes less straightforward than it first appears. Still, our minds keep reaching for a master clock. It is a very human instinct. We like one answer, we like one schedule, we like one neat line running from past to future with everyone arranged along it. Relativity asks us to replace that picture with something more careful. Local time is clear. Your clock measures your time. A nearby clock moving with you agrees. A shared frame can be built for observers moving together. But across great distances, speeds, and gravitational conditions, the idea of one universal present becomes fragile. There is a comforting side to this, though it may take a while to notice. Relativity does not take time away from us. It makes time more physical. It says that time is not an invisible command issued from outside the universe. It is woven into the universe itself, shaped by motion and gravity, measured by real clocks on real journeys. It belongs to the same world as planets, stars, light, and bodies. In that sense, time is not less real because it is relative. It is more deeply connected to everything else. Think again of the bedside clock. It seems simple, but it is part of Earth's rotation, Earth's gravity, the motion of the planet around the sun, the motion of the solar system through the galaxy, and the broader expansion of the cosmos. Your little clock is not isolated from the universe. It is quietly taking its path through it. So are you. You may feel still in your room, but you are moving with Earth, carried around the sun, carried through the Milky Way, carried within a universe whose distant galaxies are receding as space expands. And through all of this, your body keeps its own time. Heartbeats, breaths, thoughts, sleep, memory. A local rhythm inside a much larger relativistic reality. Einstein's clock, then, is not one clock. It is every clock understood properly. It is the watch on a wrist, the pulse in a body, the atomic clock in a laboratory, the timing signal in a satellite, the aging of a particle, the slow tick near a massive star. Each one tells the truth of its own path. Where you stand matters, how you move matters, how deep you are in gravity matters. Time is not handed down equally from above, it is measured from within. This is why the question of cosmic time must be approached gently. The universe can be described as having an age, but that age is not the same thing as a single universal, now that overrides all observers. Cosmologists can define a useful time for the large-scale universe by imagining observers moving with the general expansion, but that is a special and practical choice, not a return to Newton's absolute river. It works because the universe, averaged over immense distances, has a common history of expansion and cooling. But inside that history, local clocks still have their own paths. As we move outward from Earth and begin thinking about galaxies separated by enormous distances, the issue becomes even stranger. It is not only that clocks can tick at different rates, it is also that different observers can disagree about which distant events are happening at the same time. The present, which feels so solid in a quiet room, becomes harder to define across the cosmos. The word now begins to shrink into something local, something nearby, something shared only by observers close enough and similar enough in motion for the question to behave. Beyond that, the universe does not provide a simple master slice called the present. It gives us light cones, histories, signals, distances, and clocks that speak honestly from their own journeys, but not one grand cosmic clock face on which every event can be pinned at once, and that is where the next step naturally waits. Once time depends on motion and gravity, the old idea of one universal present starts to loosen. A clock can tell you what time it is here. A telescope can show you what time it was when distant light left its source. Cosmology can tell us how old the universe is in a carefully defined sense. But the simple question, what is happening right now everywhere, turns out to be far less simple than it sounds. Because in a relativistic universe, there may be no single, now large enough to cover everything. Once time depends on motion and gravity, the word now begins to behave less like a solid floor, and more like a small patch of ground beneath your feet. It is perfectly useful where you are. It tells you that the room is quiet now, that your clock shows this hour now, that your thoughts are here now, moving gently from one idea to the next. But when we try to stretch that same now across the whole universe, from Earth to distant galaxies, from your bedside to stars whose light began travelling before humans existed, the word starts to lose its simple meaning. It is not that the universe becomes disorderly or vague. It is that our everyday idea of a shared present was built for nearby things, for rooms and roads and voices, not for a cosmos where light itself needs time to carry news from one place to another. In ordinary life, we do not notice this problem because the distances around us are small and light is extremely fast. When someone across the room waves, you see it almost instantly. When a lamp turns on, the room brightens without any delay you can feel. If two people clap at the same time in a small hall, you and a friend standing nearby will usually agree that the claps happen together. There may be tiny differences in when sound reaches each ear, but those are practical details, not deep cosmic troubles. Human beings evolved in a world where signals arrive quickly enough that the present seems shared. That makes the idea of now feel obvious. We assume there is a single moment passing everywhere, and we are all riding along inside it. But physics asks us to slow down and pay attention to how we know anything is happening at all. You know an event has happened because some signal reaches you. Most often, in astronomy, that signal is light. A star brightens, and light travels outward. A galaxy spins, and light from its stars crosses space. A supernova explodes, and the news of that explosion travels at the speed of light. No matter how dramatic the event is, the information does not arrive instantly. The universe does not send notifications faster than light, which is probably for the best considering how many notifications we already have. Instead, every observation of a distant object is also an observation of the past. The moon is close by cosmic standards, but even its light takes a little time to reach us. The sun is farther away, and sunlight takes several minutes to arrive. When you feel sunlight on your face, you're feeling energy that left the sun earlier, not at the exact instant you notice it. The planets are seen with delays that change as they move. The nearest stars are seen as they were years ago. Galaxies may be seen as they were millions or billions of years ago. Looking outward is also looking backward. A telescope is not only a device for seeing far away, it is a machine for receiving old light. This alone would make the present difficult, but relativity makes the difficulty deeper. It is one thing to say we see distant things as they were, because light takes time to travel. That part is already strange, but it still lets us imagine that those distant places have a current state somewhere out there, even if we cannot see it yet. We might picture a galaxy as it is right now, at this very moment, and imagine that its light will arrive later. That picture feels natural. But Einstein showed that the phrase "at this very moment" is not universal when the distant galaxy is far away and observers can move differently. Different observers can slice space and time into past, present and future in different ways. They can disagree about which distant events are simultaneous, even though each observer is using clocks and rulers correctly. This is called the relativity of simultaneity. The phrase sounds technical, but the idea can be approached gently. Simultaneity means two events happening at the same time. In the old view, that seemed simple. Either two things happened together or they did not. If lightning struck two trees at once, then everyone, in principle, should agree that the strikes were simultaneous, once they corrected for the travel time of the light. But in special relativity, observers moving relative to one another can make those corrections and still disagree about whether the events happened at the same time. One observer may say the two strikes were simultaneous. Another, moving steadily relative to the first, may say one happened before the other. Neither is confused. Neither forgot to account for light travel time. The disagreement comes from the structure of space and time itself. A classic way to picture this uses a train, because physics has always had a soft spot for trains. Imagine a long train moving smoothly past a platform. A flash of light occurs at the front of the train, and another at the back. Someone standing at the middle of the platform receives both flashes and, after accounting for the equal distances involved in their own frame, concludes that the flashes happened at the same time. But someone standing at the middle of the moving train is moving toward one flash and away from the other. Because light has the same speed for both observers, the train observer receives the flashes at different times and concludes that they were not simultaneous in the same way. The details can be worked out precisely, but the core lesson is enough for now. Events that one observer calls simultaneous may not be simultaneous for another observer in motion. That is unsettling because we usually treat the present as a universal slice through reality. We imagine everything that exists now as if the universe were a loaf of bread and now a one clean slice from end to end. Earth now, Mars now, a galaxy now, a black hole now, all belonging to the same cosmic layer. Relativity says that different observers cut the loaf at different angles, at least when dealing with events separated by distance. Close by, the slices are almost the same. Far away, even a small difference in motion can make the meaning of now shift dramatically. Across the span of the observable universe, the shift can be enormous. This does not mean causality breaks. Causes still come before effects where it matters. You cannot receive a reply before you send the message, and you cannot see a star explode before the light from the explosion has had time to arrive. Relativity protects the order of events that can influence one another. If one event can cause another, all observers agree on that causal order. The disagreement appears for events that are so far apart and so separated in time that light could not travel from one to the other in time to connect them. Such events are outside each other's immediate influence. Their order can depend on the observer. That is not a loophole for chaos. It is a boundary on what now can mean. This boundary is deeply connected to the speed of light. Light is not just fast, it is the fastest way information can travel through the universe, as far as physics tells us. Because of this, every observer has a region of possible influence and possible knowledge. There are events whose light has reached you. They belong to your observable past. There are events you could influence someday by sending a signal, if enough time passes. They belong to your possible future. But beyond those regions are events that are too far away to be connected to you yet. They are not part of your past or future in any practical causal sense. To call them happening now is to choose a way of organizing space and time, not to identify a universal fact that all observers must share. This is where the idea of no cosmic now becomes clearer. There is no single present moment stretching across the entire universe that every observer can agree on. There are local presents. There are nearby regions where clocks can be synchronized well enough for practical purposes. There are reference frames, carefully chosen ways of assigning times to distant events. There is even a very useful cosmic time in cosmology, which we will come to more fully, based on observers moving with the large-scale expansion of the universe. But none of these is the same as an absolute now built into reality for everyone, everywhere. In daily life, we synchronize clocks by sending signals. We agree that this clock and that clock show the same time after correcting for the time it takes a signal to travel between them. This works beautifully over small distances and in shared conditions. It is how networks, laboratories, navigation systems and daily schedules operate. But on cosmic scales, synchronization depends on assumptions about the observer's state of motion and the path of signals. There is no way to step outside the universe and set all clocks at once from a privileged viewpoint. Every method of assigning distant times belongs to a framework inside the universe. Astronomy gives us a practical version of this problem every night. Suppose a star in a galaxy far away collapses and explodes. If that galaxy is 10 million light-years away, we will see the explosion 10 million years after it happened according to the usual distance language. On Earth, we might say the supernova is happening tonight because tonight is when its light arrives in our telescopes. But we also say it actually happened 10 million years ago. Both statements make sense in different ways. One refers to our observation, the other refers to a time assigned within a cosmological model that accounts for the light travel time. But asking what is happening in that galaxy right now is harder. We can calculate an answer within a chosen frame, but we cannot observe it now, and a different observer moving differently may assign a different set of distant events to the present. The farther away we look, the more our view becomes a layered record of different cosmic ages. Nearby stars show us the relatively recent past. More distant galaxies show us earlier times. The deepest observations show galaxies as they were when the universe was young. In a sense, the night sky is not a single photograph of the universe at one moment. It is a collection of messages from many times. It is more like opening letters that have been travelling for different lengths of time. Some were mailed yesterday, some before your grandparents were born, some before Earth had complex life, and some from an era when the first galaxies were still assembling. The sky looks spatial, but it is also historical. This is one reason cosmologists must be careful when building a map of the universe. They do not simply map where things are. They map where things were when the light left them, then interpret that information through models of expansion, gravity, and cosmic history. Distant galaxies are not only far away, they are young versions of themselves. We see them at earlier stages of development. A galaxy whose light has travelled for billions of years may, by now in a chosen cosmic frame, be much older, changed, merged, dimmed, or no longer recognizable in the same form. But its present condition is not directly available to us. The universe shows us its archive, not its live broadcast. The absence of a universal now can feel like a loss at first. Our minds like the thought that somewhere at this exact moment, all things are arranged in one definite cosmic state. There is Earth as it is now, distant stars as they are now, galaxies as they are now, everything lined up in a grand, instantaneous inventory. Relativity does not forbid us from making such an inventory within a chosen coordinate system, but it tells us not to mistake that inventory for the one true present of the universe. Another observer, moving differently, can draw a different inventory. The physical events are real, the relationships of cause and signal are real. But the slicing into one global now is not uniquely dictated by nature. This may sound abstract, so let us bring it into a more familiar comparison. Think of a city viewed from different streets. There is a real city. The buildings are real, the roads are real, the distances are real. But the view from one street lines up landmarks in one way, while the view from another street lines them up differently. A tower may appear beside a church from one angle and far away from it from another. The city has not changed, but the way you project it into a view depends on where you stand. In relativity, spacetime is the real city. The present moment is more like a viewpoint, a way of slicing and arranging distant events. Local experience remains firm, but the global arrangement depends on the observer. Another helpful comparison is a book, though it must be used carefully. Imagine the whole history of the universe as a very large book. We experience it page by page, sentence by sentence. Presentism, the everyday feeling, says only the current word is real. The past has been read and is gone. The future has not been printed yet. Relativity seems friendlier to a different picture, sometimes called the block universe, where past, present and future are all part of the four-dimensional structure. In that picture, different observers may disagree about which distant events share a page called now, because their motion gives them different ways of cutting through the book. This does not mean your choices are fake or your experiences do not matter. It simply means the physics of time does not provide a universal spotlight moving across the whole cosmos. Some people find the block universe unsettling because it seems to freeze time, but physics does not require us to settle every philosophical question tonight. For our purpose, the practical lesson is enough. The present is not a cosmic sheet sweeping across everything. It is local, frame-dependent, and tied to how observers move. Our feeling of a flowing now is real as an experience, and it organizes our lives beautifully. But it is not a feature that scales neatly to the whole universe. There is still a special sense in which cosmology speaks of the universe now. Scientists can describe the current age of the universe, the current average temperature of the cosmic microwave background, the current rate of expansion, and the current large-scale arrangement of matter. This is possible because the universe, on very large scales, has a natural reference frame connected to its expansion. Observers who see the cosmic microwave background as nearly the same temperature in all directions are often treated as being at rest with respect to the cosmic expansion. In that frame, one can define a cosmic time. It is an extremely useful tool. It lets scientists say the early universe was hot and dense, that atoms formed later, that galaxies formed later still, and that today the universe is in a relatively mature star-filled era. But useful does not mean absolute in the old sense. Cosmic time is like choosing a very sensible map for a very large territory. It is not arbitrary, because it is based on real features of the universe. But it also does not undo relativity. A spaceship moving rapidly through the universe would not share the same clock reading in the same simple way. A clock near a massive object would differ from one drifting in emptier space. Local conditions still matter. The cosmic frame gives us a powerful average description, not a magical master clock hung outside existence. This distinction matters when people ask how old the universe is. The answer, about 13.8 billion years, refers to cosmic time measured by idealized observers, moving with the expansion from the early hot state to today. It is not the amount of time experienced by a photon of ancient light, because light does not have a normal rest clock in the way matter does. It is not the time measured near every black hole or by every fast-moving particle. It is the age of the universe in the standard cosmological frame, and it is one of the great achievements of modern science that this frame can be defined and tested so well. The lack of a cosmic now also changes how we think about distance. When we say a galaxy is billions of light years away, the statement can hide several meanings. There is the time its light has travelled. There is the distance it was from us when the light began the journey. There is the distance it would be assigned now in the cosmological model after space has expanded while the light was travelling. These are not always the same. Expansion stretches space during the journey, so cosmic distances require careful language. Once again, the universe refuses to behave like a simple stage with objects fixed at ordinary distances while one shared clock ticks above them. And yet, none of this makes the universe unknowable. It makes it more interesting, but not impossible. Scientists can still reconstruct cosmic history by combining observations with the rules of relativity, gravity, light, and matter. In fact, the absence of a universal now is not a barrier to knowledge. It is part of the knowledge. We learn the universe by accepting that observation arrives through time. We look at ancient light and infer what the cosmos was like when that light began travelling. We compare many observations at many distances and build a timeline of expansion and structure formation. The result is not a live snapshot, but a deeply layered history. There is something calming about this if we let it be calming. The universe does not demand that everything happen in one shared present. It allows each place, each clock, each observer to have a local rhythm. Your now is real here. A distant galaxy's now is not something you can simply reach across space and point to without choosing a frame. The stars above are not all showing you the same universal moment. They're showing you a mixture of old departures, signals sent across darkness, each arriving in your present after travelling through its own long silence. When you look up, you're not seeing the universe as it is all at once. You're seeing the universe as it has been, delivered to you at the speed allowed by nature. That may be why the night sky feels so different from a clock face. A clock face tries to gather time into one clear answer. The sky spreads time out. It lets you see delay, distance, history, and change all at once. A star may be gone by the time its light reaches you. A galaxy may have transformed. A cluster may have shifted. The light is still real. The view is still true, but it is truth carried from another time. So when someone asks what is happening right now at the edge of the observable universe, the best scientific answer begins with care. Right now according to which observer, right now in which frame. Right now based on which method of assigning time to a place whose current light cannot yet have arrived. These are not evasions. They are the honest grammar of relativity. The universe has no central clock room, no universal bell, no master presence sweeping across all galaxies. It has events, signals, histories, and relationships. It has local clocks telling local truths. It has a large-scale cosmic time that helps us describe its evolution. But it does not have one single now that everyone everywhere must share. In a quiet human life, this is easy to forget, and perhaps it is healthy that we do forget it most of the time. We need our local now. We need breakfast now, sleep now, kindness now, the next breath now. A person cannot live by constantly correcting for distant simultaneity. Imagine trying to make plans with a friend and saying you will meet at 7, relative to your shared motion through space-time, and after accounting for the cosmological frame. You may be scientifically thoughtful, but you will probably be eating alone. Local time is one of the great practical gifts of the universe. It works well enough for life. The deeper view does not replace that local time. It surrounds it. It reminds us that the present moment, so intimate and obvious from the inside, is not a cosmic command. It is a nearby agreement, a small region of clarity carried along a path through space-time. Beyond that region, light must travel, clocks may differ, and observers may disagree about simultaneity without anyone being wrong. The universe is not less real because it lacks a single present. It is simply larger than the human habit of imagining one. This prepares us for the next question. If there is no universal now in the old absolute sense, how can scientists still say the universe has an age? How can they measure time since the beginning, if time depends on observers? The answer lies in the large-scale order of the cosmos, in the expansion of space, in ancient light that fills the sky, and in a special kind of clock defined not by a wall, a wrist, or a satellite, but by the shared history of the universe as it cooled from its earliest visible state into the vast structured cosmos we observe tonight. To measure an age, you usually need two things. You need a beginning that can be described clearly enough, and you need a clock that has kept some kind of trustworthy record since then. This is easy enough for a person, at least in the ordinary way. A birth certificate gives a date, a calendar counts the years, and eventually someone puts candles on a cake and politely pretends not to notice the increasing fire hazard. For a tree, you can count rings. For a rock, you can look at the slow decay of atoms locked inside it. For an old building, you can examine its materials, its records, its style, and perhaps the number of very suspicious creaks it makes in the night. But the universe is not a person, a tree, a rock, or a building. It did not leave a neat label saying made on this date. There was no outside observer standing nearby with a clipboard, no cosmic midwife noting the hour, no little tag attached to the newborn cosmos reading "Please handle with care, extremely hot." And yet scientists can say, with impressive confidence, that the universe is about 13.8 billion years old. That number has become so familiar in science writing that it can slip past us too quickly. 13.8 billion years, not 13.8 billion years since Earth formed. Earth is much younger. Not 13.8 billion years since the first stars lit up. Stars came later. Not even 13.8 billion years since light first began moving, because light and energy were present in the early universe in ways that are not as simple as a beam travelling freely through empty space. The age of the universe means the time, in the standard cosmological sense, since the early hot, dense state from which the observable universe expanded and cooled. It is the age measured along the kind of cosmic clock we began to approach earlier, the clock of observers moving with the overall expansion of space. That phrase matters. The universe is not being timed by one absolute clock in the old Newtonian way. Instead, cosmologists use a natural and useful way of measuring time based on the large-scale structure of the universe. Imagine observers spread throughout space, not racing through it in unusual directions, not circling black holes, not being thrown around by local disturbances, but drifting with the expansion itself. These observers are often called co-moving observers, although we can simply think of them as riders carried along with the cosmic flow. Each one has a clock. Each one sees the universe around them expanding, cooling, and changing in a broadly similar way when averaged over enormous distances. The time measured by those clocks is what scientists mean by cosmic time. This does not erase relativity. It does not bring back a magical universal now for every possible observer. A fast-moving spacecraft or a clock near a compact massive object would still measure time differently. But because the universe as a whole has a large-scale smoothness, cosmic time gives us a way to describe its shared history. It is like choosing the most sensible calendar for the whole ocean by following the tides, even though every wave and boat and drifting leaf has its own little motion. The calendar is useful because the ocean has patterns. The universe has patterns too. It expanded, it cooled. Its light stretched, its matter gathered. Those changes let us count. One of the greatest clues in that counting is ancient light. Not the first light in the sense of the first glow that ever existed, because the early universe was filled with radiation from the beginning of the hot, dense phase. Rather, it is the first light that could travel freely across space without constantly being scattered. This ancient light is known as the cosmic microwave background. It is sometimes described as the afterglow of the early universe, a faint bath of radiation arriving from every direction in the sky. It is not visible to human eyes. If you look up at night, you will see stars, planets, perhaps the moon, perhaps the soft smear of the Milky Way if the sky is dark enough. You will not see the cosmic microwave background directly, but radio instruments and space telescopes can detect it. It fills the universe like a very cold whisper left over from a time when everything was much hotter. To understand why this light matters, it helps to picture the early universe not as an explosion into empty space, but as space itself expanding from a hot, dense condition. In the beginning, the observable universe was not full of stars and galaxies. There were no planets, no atoms in the familiar sense, no quiet regions of darkness between shining objects. The universe was a blazing mixture of particles and radiation, so hot that electrons could not settle down with atomic nuclei to form neutral atoms. Light existed, but it could not travel freely for long. It kept running into charged particles. Photons, the particles of light, were scattered again and again, like a person trying to cross a crowded room, while everyone keeps gently bumping into them and saying sorry. The universe was bright, but not transparent. As expansion continued, the universe cooled. This cooling is central to cosmic history. The universe did not cool because it lost heat to some outside space. There is no outside kitchen counter on which the universe sat cooling after being removed from the oven. It cooled because space expanded, stretching radiation and lowering the energy of the cosmic contents. After about 380,000 years, the temperature had fallen enough for electrons and nuclei to combine into neutral atoms, mostly hydrogen and helium. Once that happened, light was no longer constantly scattered by free-charged particles. The cosmic fog cleared. Photons could travel through space. The universe became transparent. That moment is sometimes called recombination, though the name is slightly misleading because it sounds as if atoms had combined before and were combining again. It's also sometimes called the surface of last scattering, a phrase that means the place and time from which the ancient light last scattered, before travelling freely toward us. In a sleepier mood, we might call it the moment the universe finally let its light go. This is the first light we can observe directly, not because nothing happened before it, but because earlier light could not cross the young universe in a straight free journey to reach us. The cosmic microwave background is therefore like the oldest photograph the universe allows us to take. It is not a photograph of the very beginning, but of the time when the universe first became transparent. This is important because looking at the cosmic microwave background gives scientists a baby picture of the universe. A very unusual baby picture, admittedly. Most baby pictures do not cover the entire sky, require space telescopes, or show tiny temperature variations that later grew into galaxies. Still, the comparison works. The cosmic microwave background shows the universe when it was only about 380,000 years old, which sounds ancient until you compare it with 13.8 billion years. On the cosmic scale, it is infancy. The light has been travelling ever since, stretched by the expansion of space from a hot glow into cold microwave radiation. When instruments measure it today, they are receiving a message sent when the universe was young enough that stars had not yet formed. The pattern in that ancient light is one of the reasons scientists can estimate the age of the universe. The cosmic microwave background is not perfectly uniform. It is almost the same in every direction, but not exactly. There are tiny variations in temperature, slightly warmer and slightly cooler patches. These differences are very small, but they are enormously meaningful. They are the fingerprints of early density variations, places where matter was a little more or a little less concentrated. Over time, gravity amplified those tiny differences. Slightly denser regions pulled in more matter. Clouds formed. Stars were born. Galaxies gathered. The large-scale structure of the universe, with its clusters, filaments, and voids, grew from those early irregularities. By studying the size, distribution, and strength of the patterns in the cosmic microwave background, scientists can infer what the universe contained and how it expanded. How much ordinary matter there was, how much dark matter, how much dark energy, how fast expansion was proceeding at different stages. These ingredients affect the growth of structure and the stretching of light. They also affect the calculated age. The age is not guessed by simply staring into the sky and saying, well, it looks very old. It comes from fitting many pieces of evidence into a coherent model of cosmic evolution. Another clue comes from the expansion of the universe itself. Distant galaxies are, on average, moving away from us, not because we are at the centre, but because space between galaxies is expanding. This was one of the great discoveries of the 20th century. The farther away a galaxy is, the more its light is shifted toward longer wavelengths, a sign that space has expanded during the light's journey. If the universe is expanding now, then in the past it was denser and hotter. Run the story backward carefully and you approach an earlier state when everything in the observable universe was packed much more tightly together. The rate of expansion, combined with the contents of the universe, helps determine how much time has passed since that early hot, dense condition. It is tempting to imagine this as rewinding a movie all the way to a single frame labelled the beginning. But the real calculation is more careful. The expansion has not necessarily proceeded at the same pace throughout all cosmic history. Gravity from matter slowed expansion in the past. Dark energy appears to be speeding expansion today. Radiation mattered more in the early universe than it does now. Matter and energy changed in relative importance as space grew. The age of the universe depends on this whole expansion history. It is not just a matter of taking the current expansion rate and dividing in a simple way. The universe has had different eras, each with its own influence on the cosmic clock. Still, the basic idea remains approachable. The universe has been expanding and cooling. We can observe how fast it's expanding now. We can observe ancient light from when it was young. We can observe the distribution of galaxies and clusters. We can measure the abundance of light elements like hydrogen and helium, which were forged in the early hot universe. We can compare all of this with the predictions of cosmological models. When the evidence lines up, the age emerges. The answer is about 13.8 billion years. There is a gentle subtlety here. That age is not counted since the cosmic microwave background was released. The cosmic microwave background comes from when the universe was already about 380,000 years old. Compared with 13.8 billion years, that is a small early interval, but it is not nothing. So if we are speaking precisely, the cosmic microwave background is not the starting gun of the universe. It is the earliest directly visible light, the oldest freely travelling signal we can observe. It helps us count back toward the beginning, but the age of the universe includes the time before that light was released. We infer those earlier phases through physics, not by seeing them with ordinary light. This distinction is rather like learning about someone's early childhood from a first photograph taken when they were a few months old. The photograph is not from the moment of birth, but it still contains clues. It shows the child at an early stage. It confirms that they existed by then. It may reveal features that connect to later development. Combined with records, biology, and family history, it helps reconstruct the timeline. The cosmic microwave background is the universe's earliest family photo, and scientists have examined it with a level of care that would make even the most enthusiastic grandparent seem casual. One of the striking things about the cosmic microwave background is how uniform it is. Its temperature is nearly the same across the sky. This tells us that the early universe was remarkably smooth. Not perfectly smooth, because then galaxies might never have formed, but smooth enough to raise deep questions. Regions of the sky far apart appear to have nearly the same temperature, even though, in a simple early picture, they might not have had time to exchange signals and come into balance. This puzzle is one reason scientists developed the idea of cosmic inflation, a very early period of extremely rapid expansion. Inflation is not needed in detail for tonight, but the rough idea is that a tiny region of the early universe may have expanded enormously, making the observable universe appear smooth, while also stretching tiny quantum fluctuations into the seeds of later structure. It is a bold idea, and scientists continue to study its details, but it helps explain why the ancient light looks the way it does. The cosmic microwave background also gives us a preferred frame in a practical sense. If you move through this background radiation, it appears slightly warmer in the direction you're moving and slightly cooler in the opposite direction, like feeling a wind on your face as you move through still air. Earth, the Sun, and our galaxy all have motions relative to this background. Scientists can measure that motion by looking at the tiny directional temperature difference. Once corrected for this motion, the background looks extremely uniform. This gives cosmologists a natural way to define the cosmic rest frame, the frame in which the ancient radiation has no overall dipole pattern from motion. This frame is not absolute time returning from exile. It is a physically meaningful reference frame provided by the contents and history of our universe. It is the frame in which cosmic time is especially natural. From that point of view, the age of the universe is the time elapsed for ideal observers who have been moving with the expansion since the early universe. Such observers would see the cosmic microwave background as broadly uniform around them, not strongly hotter in one direction because of their own motion. Their clocks define the cosmic age. In this frame, we can say the universe was once 380,000 years old when it released the light we now detect. It was a few 100 million years old when the first stars began to shine. It was several billion years old when galaxies matured in great numbers. It was about 9 billion years old when the Sun and Earth formed. It is now about 13.8 billion years old in this cosmic accounting. Notice how this preserves both truths at once. Relativity says there is no universal now that all observers must share. Cosmology says there is still a natural cosmic time for describing the average history of our expanding universe. These are not enemies, they are different levels of description. Relativity gives the rules for time, motion, gravity, and observation. Cosmology applies those rules to a universe that, on very large scales, is smooth and expanding. The result is a cosmic clock that is not absolute in the old philosophical sense, but is real and useful in the scientific sense. The age of the universe is also checked against the ages of things inside it. Stars provide important tests. Some stars are very old, especially those in globular clusters, which are dense ancient groups orbiting galaxies. By studying how stars burn their fuel and evolve, astronomers can estimate their ages. The oldest stars must be younger than the universe itself. If a model of cosmic age made the universe younger than its oldest stars, something would be wrong, rather like claiming a parent is younger than their child, which would make for a difficult family dinner. Modern estimates broadly agree. The oldest stars fit within a universe about 13.8 billion years old. Radioactive dating also helps with objects in the solar system, though Earth and meteorites are much younger than the universe. The solar system formed about 4.5 billion years ago, long after the first generations of stars. The elements in planets and bodies like ours were made through earlier cosmic processes. Hydrogen and helium came mostly from the early universe. Heavier elements were forged in stars and stellar explosions. By the time Earth formed, the universe had already lived through many stages of matter gathering, stars burning, and galaxies evolving. We are late enough for chemistry to be rich, but not so late that the stars have faded away. There is something profound in that timing, though we do not need to dress it up too much. A universe too young would not have had time to make planets like Earth, or carbon, oxygen, iron, and the other ingredients that life uses. A universe much older might be quieter, with fewer bright stars forming, depending on how far ahead we imagine. We exist in an era when cosmic history has produced complexity and still offers light. The age of the universe is not just a number in a textbook. It is the background condition that made every ordinary moment possible. The reason your body contains heavy elements is that the universe had time before you. The reason the night sky contains galaxies is that gravity had time to gather matter. The reason there is ancient microwave light to measure is that light has had nearly the whole age of the universe to travel. This brings us back to the phrase first light. There is a slight poetic danger in it, because it can make the young universe sound dark before that moment, as if someone finally switched on a lamp. That is not quite right. The early universe was full of radiation. It was intensely bright in a physical sense. But it was opaque. Light could not travel freely across large distances. The release of the cosmic microwave background was less like a lamp turning on, and more like a fog lifting. The light was already there, but after atoms formed, it could move freely. Space became transparent. From then on, photons streamed across the expanding universe. Their wavelengths stretched over billions of years until they became the cold microwave background we detect today. So when we count time since the earliest visible light, we are really using that light as a marker. It says, by this moment the universe had cooled enough to become transparent. It gives us a precise window into conditions at that time. It anchors the timeline. From there, we connect backward to the hotter earlier phases and forward to the formation of structure. The ancient light is a timestamp, not the birth itself. It is a note left near the beginning of the archive, written in temperature patterns across the sky. And what an archive it is. Each patch of the cosmic microwave background carries information about the early plasma, the mixture of radiation and matter before atoms formed. Tiny variations reveal sound waves that move through that plasma, shaped by gravity and pressure. These ancient patterns remain visible as slight differences in temperature. In a very real sense, the early universe had a kind of ringing structure, a pattern of compressions and rarefactions, and the cosmic microwave background preserves it. Scientists do not hear it with ears, of course. They read it through maps, statistics, and careful instruments. But the image is still lovely in a plain scientific way. The universe's first clear light carries traces of its early vibrations. As that light travelled, space expanded. Expansion stretched it from a hot visible and infrared glow into microwaves. This stretching is not the light getting tired, as an old discarded idea once suggested. It is a consequence of the expansion of space itself. The wavelength grows as space grows. The universe has not merely aged around the light, it has changed the light during the journey. By measuring that change, scientists learn how much the universe has expanded since the light was released. That expansion factor is another key part of reconstructing the cosmic timeline. All of this turns the universe into its own clock, not a clock with hands, not a clock with a face, not even a clock that ticks in one place. Its clock is the changing relationship between expansion, temperature, matter, radiation, and structure. The universe was hotter when smaller, cooler after expanding, smoother at early times, clumpier later, more dominated by radiation early on, more shaped by matter afterward, now increasingly influenced by dark energy. Each stage leaves evidence. The ages read from the whole pattern. like a skilled naturalist reading a landscape and knowing where the river once flowed. There are still tensions and open questions in modern cosmology. Measurements of the current expansion rate using different methods do not all agree perfectly. Some methods rely on the early universe and the cosmic microwave background. Others rely on distance measurements in the more recent universe, using stars and supernovae as markers. The difference is an active area of research. It may point to unknown errors in measurement, or it may hint at new physics. Even so, the broad age of about 13.8 billion years remains a strong and widely supported result. Science is rarely a frozen monument. It is more like a carefully maintained garden, with strong trees, new shoots, and the occasional stubborn weed that refuses to explain itself. For the calm path we're walking here, the essential point is this. The universe can have an age even though it does not have a single universal present in the old everyday sense. That age is counted using cosmic time tied to the large-scale expansion. The oldest light we can observe, the cosmic microwave background, gives us a powerful early timestamp from when the universe became transparent. By combining that ancient light with measurements of expansion, matter, radiation, and structure, scientists count the time from the early hot, dense universe to now in the standard cosmic frame. And now, here we are, inside that age. Not outside it, not looking at it from a safe balcony, but made from its consequences. The calcium in bones, the iron in blood, the carbon in cells, the oxygen in each breath, all belong to a universe that had time to make stars and let some of them die. The light from the cosmic microwave background has been travelling longer than Earth has existed, longer than the sun has shone, longer than galaxies have had their present shapes. It passes through the room, around you now, faint and cold, unnoticed by the body but measurable by instruments. While your local clock keeps the hour beside you, the ancient light keeps telling the older story. That older story is not only about how long the universe has existed, it is about how time itself is tied to expansion. A static universe would give a very different sense of cosmic history. Our universe is not static. Space grows, light stretches, densities fall, temperatures drop. The contents of the cosmos change their behaviour as the scale of space changes. So the next step is to follow that connection more closely, to ask how an expanding universe keeps its rhythm, and why cosmic time is not just a number counted from the past, but a measure of the ongoing growth and cooling of everything we can observe. An expanding universe keeps time in a way that is very different from a clock on a wall. A wall clock stays in one place, or at least it seems to, and marks the seconds with tidy repetition. The universe does not do that. It does not have hands, numbers, bells, or a polite little tick that tells galaxies when to begin their morning. Its rhythm is written into expansion, cooling, light stretching across space, matter thinning out, and structures slowly forming under gravity. If we want to understand what time means for the cosmos, we have to stop imagining time as something simply counted beside the universe, and start seeing it as something read from the changing state of the universe itself. The key idea is that space is expanding. This does not mean galaxies are flying away from a central point into empty surroundings, like fragments from a firework. That image is tempting, but it leads the mind in the wrong direction. The Big Bang was not an explosion at one location inside a larger room. It was the beginning of the hot, dense, expanding state of space itself, at least as far back as our current physics can confidently describe. Every region of the observable universe was once much closer to every other region. As time passed, the distances between large-scale regions grew. Space did not expand into something in the ordinary sense. Space itself was the thing changing. This is a difficult idea because ordinary expansion always seems to need an outside. A balloon expands into the room around it. Bread rises inside an oven. Steam spreads into the air. But the universe is not an object sitting inside a larger container, or at least not in any way our measurements require. When cosmologists say space expands, they mean that the distances between far apart galaxies increase because the geometry of space changes with time. The galaxies are not necessarily moving through space in the usual local sense. Rather, more space appears between them as the universe evolves. On the larger scales, the whole cosmic map stretches. A simple comparison is raisin bread dough rising in an oven. Imagine raisins embedded in the dough. As the dough expands, every raisin sees the other raisins moving away. No raisin has to be the center. From each raisin, the others recede. The farther away a raisin is, the faster it appears to be carried away by the expansion of the dough between them. This is not a perfect comparison, because dough expands into an oven, and the universe is not dough, though it would certainly be easier to study if it were. But the picture helps with one important point. Expansion can make every place see distant places receding without any one place being special. The same thing happens in the cosmos. From our galaxy, distant galaxies appear to recede. From one of those galaxies, we would appear to recede. From another galaxy far away, the same pattern would appear there too. This does not mean Earth is central, it means expansion is a property of the whole large-scale universe. Every observer moving with the cosmic flow sees the same general pattern. Nearby objects may have their own motions, because gravity pulls galaxies around within groups and clusters, but once we average over enormous distances, expansion becomes the dominant pattern. This is where cosmic time gains its meaning. If there are observers drifting with that overall expansion, not moving strongly in any special direction compared with the cosmic background, then their clocks can mark the age of the universe in a shared way. These clocks are not sharing an absolute present in the old sense. They are simply following the natural flow of the expanding cosmos. Each such observer would see the universe pass through the same broad stages: a hotter, denser early state, a cooling plasma, the formation of atoms, the release of ancient light, the long dark period before stars, the first stars and galaxies, the growth of cosmic structure, the later era in which dark energy becomes increasingly important. That sequence gives the universe a rhythm. The rhythm begins with temperature. In the early universe, everything was much hotter. Space was packed with radiation and particles. As space expanded, radiation stretched. The stretching of light is one of the clearest signs of cosmic expansion. Light has a wavelength, a kind of spacing in its wave pattern. When space expands while light travels through it, that wavelength stretches too. Stretched light becomes redder, and if stretched far enough, it moves beyond visible light into infrared, microwave, and radio ranges. This is why distant galaxies often appear redshifted. Their light has been stretched by the expansion of space during its journey to us. The cosmic microwave background is the greatest example of this stretching. When that ancient light was released, the universe was much hotter, and the radiation would have corresponded to a much warmer glow. Over billions of years, expansion stretched that light until it became the cold microwave radiation we detect today. Its temperature is now only a few degrees above absolute cold, not because the light got tired, not because it lost interest halfway through the trip, but because the universe expanded around it. In this sense, the cooling of the cosmic background is a clock. The temperature of the ancient light tells us where we are in the expansion history. This kind of clock is not like a kitchen timer. It does not count down from 10 minutes and then complain because you forgot the biscuits. It is a clock based on physical change. A younger universe was smaller in the sense that distances between large-scale regions were shorter and hotter because radiation was less stretched and matter was denser. An older universe is larger, cooler, thinner, and more structured. So when cosmologists describe cosmic time, they are describing a relationship between age, expansion, temperature, density, and structure. The universe keeps rhythm by changing all these things together. There is a useful order to the changes. In the very early universe, radiation was extremely important. Radiation includes light and other fast-moving forms of energy. When the universe was young and hot, radiation helped shape the behavior of the cosmos. As expansion continued, radiation thinned and lost energy through stretching. Matter also thinned as space expanded, but matter and radiation changed in different ways. Over time, matter became more important than radiation for the large-scale gravitational story. This shift marked a major era in cosmic history. Later still, another ingredient, dark energy, became dominant in controlling the expansion. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate today. We do not yet fully understand its nature, but its effect appears to be real. This means the universe has not kept the same beat forever. Its rhythm has changed. Early on, the universe was dense and hot, with radiation playing a leading role. Later, matter guided the growth of galaxies and clusters. Today, dark energy seems to be stretching the cosmic scale at an accelerating pace. The cosmic clock does not tick evenly in the way Newton might have imagined. It has eras. It has phases. The universe is not simply older than it used to be. It is different in character. Expansion also affects density. If you take the same amount of matter and spread it through a larger volume, it becomes thinner. That is what happened to matter on cosmic scales. The early universe was dense. The modern universe, averaged across enormous distances, is extraordinarily sparse. Galaxies look grand and crowded in photographs, full of stars and glowing gas, but the spaces between galaxies are immense. Even within galaxies, stars are separated by vast distances. The universe has become a place of islands and oceans, clusters and voids, filaments and emptiness. Expansion helped create the conditions in which gravity could gather matter locally, while the overall background continued to stretch. This can sound contradictory. If space is expanding, why do galaxies hold together? Why does the solar system not expand? Why does your bedroom not become slightly larger every evening, apart from the mysterious expansion of laundry across the floor? The answer is that cosmic expansion dominates only on very large scales where gravity has not bound objects together strongly enough. Inside atoms, electromagnetic forces hold matter together. Inside planets and stars, gravity and pressure create stable structures. Inside galaxies, gravity binds stars and gas. Inside galaxy clusters, gravity can bind many galaxies together. These bound systems do not expand with the universe in the ordinary way. Expansion is not a force pulling everything apart at every scale. It is the large-scale evolution of space, most clearly seen between distant, unbound galaxies. So the cosmos has two kinds of behavior at once. Locally, matter can gather, orbit, collapse, ignite, and form structure. Globally, the space between distant structures expands. Gravity and expansion have been in a long conversation since the early universe. Slightly denser regions pulled in more matter, slowing local expansion and eventually forming galaxies and clusters. Less dense regions became voids, expanding and emptying out. The large-scale cosmic web we observe today is the result of this competition. Expansion stretches the stage, gravity gathers the actors, and the story unfolds differently in dense and empty regions. The timing of structure formation depends on expansion. If the universe had expanded too quickly in the matter-dominated era, gravity might not have had enough time to gather matter into galaxies. If it had expanded too slowly, structure might have collapsed too strongly or too early. The actual universe found a path that allowed tiny early variations to grow into galaxies, stars, planets, and eventually observers who wonder why the universe is so complicated while trying to fall asleep. The rhythm of expansion was not just background scenery, it shaped what could form and when. The first stars were born after the universe had cooled and matter had gathered into dense enough clouds. Before that, after the cosmic microwave background was released, there was a long era often called the Cosmic Dark Ages. The universe was transparent, but there were no stars yet. Hydrogen and helium filled space. gravity slowly drew matter into growing clumps. Eventually, in the densest regions, gas collapsed enough to heat and ignite the first stars. These first stars changed the universe. They produced light, forged heavier elements, influenced surrounding gas, and began the process that led to later generations of stars and galaxies. Cosmic time is marked not only by expansion, but by the events expansion permits. The formation of galaxies also belongs to this rhythm. Galaxies did not appear fully formed all at once. They grew through the gathering of gas, the birth and death of stars, and mergers with other galaxies. Looking far away lets astronomers see younger galaxies, because their light has taken a long time to reach us. Some distant galaxies look smaller, more irregular, and more active in star formation than many nearby galaxies. This is not because faraway space is naturally untidy, though it might feel that way. It is because we are seeing those galaxies at earlier times in cosmic history. Distance and time are interwoven in observation. Expansion gives the universe a visible timeline across the sky. Redshift is one of the main tools for placing objects on that timeline. The more the light from a distant galaxy has been stretched, the more the universe has expanded since that light was emitted. A high redshift galaxy is seen as it was when the universe was younger. A lower redshift galaxy is seen at a more recent stage. In this way, astronomers build a history of galaxy formation by looking across distance. The sky becomes a layered record. Nearby galaxies show a more recent universe. Distant galaxies show earlier chapters of cosmic development, though we are not using that word in the narration, only following the idea of a long unfolding record. Expansion also affects horizons. Because the universe has a finite age and light travels at a finite speed, there is a limit to how far we can observe. The observable universe includes the regions from which light has had time to reach us since the early universe became transparent, and more generally since signals could travel. But expansion complicates this picture. Some regions whose light reaches us today are now, in the cosmological model, much farther away than the travel time of the light might naively suggest, because space expanded while the light was on its way. There are also regions so distant that light emitted by them today may never reach us, because expansion carries them away too quickly for the signal to close the gap. This does not mean they are moving through space faster than light locally. It means the space between us and them is expanding in a way that can prevent future contact. That idea gives cosmic time a horizon-like quality. The universe does not simply grow older everywhere in a way we can eventually see completely. Our view is limited. As time passes, we may receive light from some regions that was already on its way, but the accelerating expansion driven by dark energy means more and more distant galaxies will slip beyond future reach. In the far future, if current understanding is right, observers in our local group of galaxies may see a much emptier sky. Distant galaxies beyond the bound local region will become increasingly redshifted and eventually unobservable. The evidence of cosmic expansion may become harder to access. The universe will still have a history, but future astronomers may have fewer visible clues. This thought is strange, but it reminds us that timing in the universe is also about access to information. The present cosmic era is special in a practical sense. We can see the cosmic microwave background. We can observe many galaxies at many distances. We can measure expansion and infer the evolution of the universe. We live at a time when the universe is old enough to contain observers and young enough that the large-scale evidence is still visible. This is not necessarily a mystical privilege. It is a scientific circumstance. The cosmic clock has hands we can read now because the universe has not yet hidden too much of its past from view. Expansion gives another meaning to the question of what time it is for the universe. The answer is not only 13.8 billion years, it is also a description of the current cosmic state. The universe is at a time when the cosmic microwave background is cold but detectable, when galaxies are mature but still forming stars, when heavy elements are common enough for rocky planets, when dark energy has become important, and when expansion is accelerating. To say what time it is for the universe is like saying what season it is. A season is not just a number of days since the year began. It is a condition of light, temperature, growth, weather, and change. Cosmic time is similar. It is the age plus the state. That is why the universe can be timed by temperature, density, and structure. Early time means hot, dense, smooth, radiation-rich. Later time means cooler, thinner, clumpier, star-filled. Much later time may mean colder, darker, more isolated, with star formation fading. The cosmic rhythm is not heard as sound, but read through these changing conditions. A clock ticks by, repeating the same action. The universe keeps time by never returning to the same state. Expansion gives it direction. Cooling gives it memory. Structure gives it milestones. There is also an important relationship between expansion and the arrow of time. The universe began in a very low entropy state, and entropy has increased as cosmic history unfolded. Expansion allowed matter and radiation to evolve, gravity to create structure, stars to form and burn, and energy to spread. The direction from hot, dense early universe to cooler, expanded later universe lines up with our experience of time moving from past to future. We remember the past, not the future. Eggs scramble, stars burn fuel, light spreads, and the universe expands. These facts are connected in deep ways. Expansion is not the whole explanation for the arrow of time, but it is part of the large-scale story in which the arrow is visible. One gentle way to think of the cosmos is as a cooling instrument. At the beginning of the observable story, it was extremely hot and dense. As it expanded, its tone changed. Radiation stretched, matter thinned, gravity gathered local structure, stars lit up, galaxies assembled, the background cooled, dark energy began to dominate the expansion. The rhythm has slowed in some senses and accelerated in others. The universe has become less uniform in matter distribution, while the average radiation bath has become colder and smoother to our instruments. It is not a simple beat, but it is a coherent progression. The cosmic microwave background is still one of the best ways to hear that progression, metaphorically speaking. Its present temperature tells us how much the universe has expanded since the light was released. Its tiny variations tell us about the seeds of structure. Its near uniformity tells us about the smoothness of the early universe. Its pattern gives clues to the mixture of matter, dark matter, radiation, and dark energy. It is both a relic and a ruler, both a photograph and a clock. It lets cosmologists connect the young universe to the present one. The expansion rate today is another part of the rhythm, but measuring it has become one of the interesting tensions in modern cosmology. Different methods give slightly different answers. Some methods infer the expansion rate from the cosmic microwave background and the standard model of cosmology. Others measure distances and motions in the more recent universe using stars and supernovae. The disagreement may come from hidden measurement difficulties, or it may be a sign that our model needs adjustment. Either way, it shows that the cosmic clock is still being studied. The broad story is strong, but the fine details remain alive with questions. This is one of the pleasant truths of science when it is working well. A good model can explain a great deal and still leave room for mystery. The expanding universe model explains the redshift of galaxies, the cosmic microwave background, the abundance of light elements, and the growth of structure. It gives us a meaningful cosmic age. But it also points toward dark matter, dark energy, inflation, and other questions not yet fully resolved. The rhythm is clear enough to follow, but not so simple that we have nothing left to learn. For someone lying quietly under a blanket, all of this may feel very far away. Expansion does not tug at the blanket. Dark energy does not stir the tea. The cosmic microwave background does not make a sound in the room. Yet all of it is part of the time you occupy. Your local clock tells you the hour. Your body clock tells you whether sleep is near. The cosmic clock says the universe is in an era shaped by billions of years of expansion, cooling, and structure formation. These clocks do not contradict one another. They operate at different scales. The personal clock, the planetary clock, the stellar clock, and the cosmic clock all belong to the same reality, but they answer different questions. So when we ask how the cosmos keeps its own rhythm, the answer is that it does so through change on the larger scale. Space expands, light stretches, the background cools, matter thins, gravity gathers what it can, stars form, shine, and die. Galaxies grow and drift apart. Dark energy pushes the expansion into a new phase. There is no master clock hanging over the universe, but there is a pattern in the way the universe evolves. That pattern lets us say not only how old the cosmos is, but what kind of cosmic era we are living in. And this brings us toward one of the most extreme tests of cosmic time. Expansion gives the universe its broad rhythm, but gravity can make local clocks behave in startling ways. If ordinary matter can slow time slightly on Earth, then very dense objects can slow it dramatically. Near neutron stars and black holes, the gentle differences of everyday relativity become severe. A clock can tick far more slowly compared with one far away. Light can struggle to escape. The meaning of time near the edge of a black hole becomes one of the strangest and most revealing parts of the whole story. Gravity is the great clock adjuster of the universe. It does not merely pull objects together, shape orbits, build stars, and keep planets from wandering off into the dark like distracted guests at a very large party. Gravity also changes the pace of time. A clock near a massive object ticks more slowly than a clock far away from it. This is true on Earth, true near the Sun, true around dense dead stars, and most dramatically true near black holes, where gravity becomes so intense that time behaves in ways that stretch ordinary language almost to breaking point. The effect begins gently enough. Here on Earth, a clock at sea level ticks a tiny bit more slowly than a clock on a high mountain. The difference is so small that no person would feel it. You cannot avoid aging by moving to a basement, though it would be a very committed strategy and probably not worth the lack of sunlight. But sensitive atomic clocks can measure the difference. The lower clock sits deeper in Earth's gravitational field, and time there passes a little more slowly compared with the clock higher up. This is not because the lower clock is damaged, tired, or under emotional pressure from being close to the laundry room. It is because gravity changes time itself. This is one of the central lessons of general relativity. Gravity is not just a force acting through space. It is connected to the shape of space and time. Matter and energy affect that shape, and objects move through the shaped geometry. The stronger the gravitational field, the more time is affected. A clock closer to a massive body does not simply appear to run slow because light takes time to reach us, or because our observations are confused. When compared carefully with a clock farther away, less time has actually passed for the clock deeper in gravity. Time has taken a different path. For ordinary planets and stars, the effect is real but usually modest. Near Earth it is small. Near the Sun it is stronger, though still not something a person could feel casually while standing nearby, partly because standing nearby the Sun is not recommended for other reasons. Around very compact objects, however, the effect grows serious. A compact object is one that has a great deal of mass squeezed into a small region. The more mass is packed into a smaller space, the deeper the gravitational well becomes. A gravitational well is a useful image. Imagine a landscape with hills and valleys. A massive object creates a kind of valley in the structure of space and time. The deeper the valley, the more strongly clocks are slowed relative to clocks far away. White dwarfs are one step into this dense territory. They are the remains of stars like the Sun, after they have shed their outer layers and left behind a hot compact core. A white dwarf can contain a mass comparable to the Sun packed into a volume roughly similar to Earth. Its gravity is much stronger than Earth's. Time on the surface of a white dwarf would run slightly slower compared with time far away, enough that the effect can be detected by careful astronomical measurements. But white dwarfs are only the beginning. Neutron stars go much further. They form when massive stars collapse after exhausting their fuel and exploding in supernovae. The remnant core becomes incredibly dense. A neutron star can contain more mass than the Sun packed into a sphere only about the size of a city. The material inside is so dense that ordinary atoms have been crushed into a state dominated by neutrons. A teaspoon of neutron star matter, if one could somehow scoop it up and bring it home, which again is not recommended and would ruin the kitchen, would have an enormous mass. The gravity at the surface of a neutron star is extreme. Time there runs noticeably slower compared with time far away. If a person could hover near a neutron star, which would require impossible protection from gravity, radiation, and several other unfriendly conditions, their clock would tick more slowly than a distant clock. Their body would also run according to that slower local time. Heartbeats, thoughts, chemical reactions, all would proceed normally from their own point of view. They would not feel time dragging. But an observer far away, comparing signals, would conclude that the person near the neutron star is aging more slowly. The same rule applies everywhere. Local time feels normal locally. The difference appears when clocks in different gravitational conditions are compared. Black holes take this effect to its most famous extreme. A black hole forms when mass is compressed so strongly that within a certain boundary nothing can escape, not even light. That boundary is called the event horizon. It is not a solid surface. You would not hit it like a wall. It is a boundary in space and time. Once something crosses inward through the event horizon, all future paths lead deeper in. Escape is no longer possible. The horizon marks the point where leaving would require moving faster than light, and nature does not allow that. From far away, the event horizon is where time becomes especially strange. Imagine watching a clock falling toward a black hole. As the clock gets closer to the horizon, its signals have to climb out of a deeper and deeper gravitational well to reach you. The light from the clock becomes stretched, shifted to lower energies, and arrives more slowly. The clock appears to tick more and more slowly. Its image fades and reddens. From your distant viewpoint, it never quite seems to cross the horizon. It appears to slow toward a frozen state near the edge, growing dimmer until it effectively disappears from view. This is one of those ideas that can make black holes sound like cosmic tricksters. From the falling clock's own point of view, however, things are different. If the black hole is large enough, crossing the event horizon may not feel like a dramatic moment locally. There may be no bright sign saying now entering black hole. Please keep arms inside spacetime at all times. The clock simply continues along its path. It crosses the horizon in a finite amount of its own time. It does not freeze from its own perspective. The freezing is what the faraway observer sees because signals from near the horizon are increasingly delayed and stretched. Both descriptions are correct within their own viewpoints. This is not a contradiction. It is relativity doing its careful work. The distant observer assigns time differently from the falling observer. The horizon is not a place where the falling clock stops for itself. It is a place where signals from the falling clock can no longer reach the outside once it has crossed. Before crossing, the signals become more and more delayed. After crossing, no signal escapes. So the faraway observer never receives a final visible moment of crossing. The falling object, meanwhile, has no option to send news back afterward. The black hole becomes a one-way region in the structure of events. This difference between viewpoints is one reason black holes are so important for understanding time. They show that time is not merely a background ticking evenly everywhere. Near the horizon, the relation between local time and distant time becomes extreme. A clock hovering just above the event horizon, if it could hover there, would tick very slowly compared with a clock far away. The closer it hovers, the stronger the effect. To hover there would require enormous acceleration, and near a real black hole the practical problems would be severe. Still, the principle is clear. Gravity can make a clock near the horizon run slower and slower compared with distant clocks. This leads to a common science fiction image. Someone spends time near a black hole and returns to find that far more time has passed elsewhere. This is not fantasy in principle. Strong gravity really can create large differences in elapsed time. Near a sufficiently massive black hole, a traveller in a carefully chosen orbit could experience much less time than people far away. The challenge is that black holes are dangerous places. Tidal forces, radiation from surrounding matter, and the difficulty of escaping or maintaining a stable path all make the situation much less convenient than a dramatic film might suggest. The universe offers time travel to the future, but it hides the ticket office in very rough neighbourhoods. Tidal forces deserve a calm explanation because they are part of what makes black holes physically severe. Gravity is stronger closer to a mass and weaker farther away. Near a black hole, the difference between the pull on one side of an object and the pull on the other can become enormous. If you fell feet first toward a small black hole, the pull on your feet could be much stronger than the pull on your head, stretching you in a process often given the oddly playful name spaghettification. It sounds like something that belongs on a menu, but it is not a pleasant dining experience. For small black holes, these tidal forces near the horizon can be deadly. For very large black holes, the horizon is much farther from the central region, and tidal forces at the horizon can be mild enough that crossing it would not immediately tear an object apart. Deeper inside, however, the situation worsens. The size of the black hole matters. A stellar mass black hole formed from a collapsed star has an event horizon only a few tens of kilometers across, depending on its mass. Near such a black hole, gradients in gravity can be fierce. A supermassive black hole like the ones found in the centers of many galaxies can contain millions or billions of times the mass of the Sun. Its event horizon can be vast. Near that horizon, tidal forces may be much gentler. This means a traveller crossing the horizon of a supermassive black hole might not notice the exact crossing by local physical sensation, though this is not an invitation to try. Once inside, no route leads back out. Black holes also affect the light around them. Light passing near a black hole can be bent strongly by gravity. This gravitational lensing can create distorted images, arcs, rings, and sometimes multiple images of background objects. Near the event horizon, light can orbit in unstable paths. Around black holes with hot gas falling in, the surrounding matter can glow intensely, forming an accretion disk. The disk may shine brightly before matter crosses the horizon, because friction, compression, and magnetic effects heat the gas to extreme temperatures. In these regions, time, light, gravity, and motion all become entangled in ways that provide real tests of general relativity. One of the striking facts about black holes is that they are not simply vacuum cleaners pulling in everything nearby. If the Sun were somehow replaced by a black hole of the same mass, Earth would not instantly be dragged inward. It would continue orbiting the same mass in much the same way, though the lack of sunlight would create other serious difficulties rather quickly. A black hole has extreme effects near its event horizon because the mass is packed into a very small region. Far away, its gravity behaves like the gravity of any object with the same mass. This is important because it keeps black holes from becoming magical monsters. They are extreme, but they obey rules. The slow clock near a black hole is one of those rules. It connects directly to the idea that time runs more slowly deeper in a gravitational well. A black hole is the deepest gravitational well nature can make in classical general relativity. Near the event horizon, the difference between time there and time far away can become enormous. From a distance, processes near the horizon appear slowed. Infalling matter appears delayed and dimmed. Signals struggle outward, losing energy. The horizon becomes a boundary between events that can still send information outward and events that cannot. This has consequences for how black holes fit into the broader age of the universe. Suppose a black hole formed billions of years ago. A clock far away in the calm cosmic background may count those billions of years in the usual cosmological way, but matter that fell close to the black hole, or crossed the horizon, has its own local history. The elapsed time along those paths may be very different. This is another reminder that the universe can have a cosmic age, while local clocks still differ dramatically. The cosmic clock describes the large-scale expansion. Black hole clocks reveal how strongly local gravity can bend that timing. There is also a deep connection between black holes and information, though we can keep it gentle here. In ordinary life, if something falls behind a wall, you might not see it, but in principle the information about it still exists somewhere. With black holes, the event horizon hides information from the outside in a more fundamental way. Classical general relativity says that whatever crosses the horizon cannot send signals back. Quantum theory adds further complications, including the prediction that black holes can slowly emit radiation and may eventually evaporate over extremely long times. This raises difficult questions about whether information is lost, preserved, scrambled, or somehow returned. These questions are still active in theoretical physics. They show that black holes are not only astrophysical objects, they are laboratories for the deepest problems involving gravity, quantum mechanics, and time. The slowest clocks in nature may not be clocks someone can hold, but physical processes occurring in extreme gravity. A particle near a black hole, a pulse of light trying to escape from near the horizon, hot gas spiraling inward. All of these are governed by local time in regions where distant time compares very differently. If an observer could watch safely from far away, they would see the near-horizon universe behaving as if slowed. The closer to the horizon the source is, the greater the delay and redshift in signals. But there is always a local story too, the story of the falling matter itself, which does not experience its own time as broken. This double viewpoint is one of the best ways to avoid confusion. From far away, the falling clock slows, fades, and never quite crosses in the visible record. From the clock's own perspective, it crosses the horizon and continues inward. Both accounts describe the same physical reality using different coordinates, different ways of slicing space and time. The event horizon is not a place where reality disagrees with itself. It is a place where our ordinary expectations about observation and time are forced to become more precise. Near black holes, the phrase, "what time is it?" becomes dependent on who is asking. A distant astronomer, a hovering observer near the horizon, and a falling observer would assign times differently. Their clocks would not keep the same pace. Their ability to exchange signals would be limited by gravity and the horizon. The local question still has an answer. The falling observer has a proper time, a time experienced along their own path. The distant observer has their own time far from the black hole. But there is no single simple time that covers both in the ordinary everyday way. This is not entirely alien to what we have already seen. Even Earth produces small differences in clock rates. The difference is that black holes make the effect impossible to ignore. They turn a subtle correction into the main event. Around Earth, relativity is needed for precise satellite navigation. Around a black hole, relativity determines the whole structure of what can be seen, what can escape, and how time itself is compared across regions. Black holes are where the quiet rules of general relativity become loud, though still in a very dignified scientific way. They also remind us that time and light are inseparable in observation. We learn about the universe through signals. If gravity stretches those signals, delays them, bends them, or prevents them from escaping, then gravity shapes not only time itself, but also our knowledge of time. A black hole does not just slow clocks near it relative to faraway clocks. It changes what distant observers can ever know about events near and inside the horizon. The horizon is a boundary of communication. Time beyond it continues locally, but it is cut off from the outside future in a very specific way. There is a calm human comparison, though it is imperfect. Imagine watching someone walk away through a thick fog while speaking to you. Their voice becomes softer and delayed. Eventually you can no longer hear them. You might know they continue walking, but their signals no longer reach you. A black hole is not fog, and the event horizon is not merely a cloudy curtain, but the comparison helps with the emotional shape of the idea. The outside universe receives less and less information from something approaching the horizon, and then none from after crossing. The object has not ceased to have its own path, it has left the communicable region. In the life of the universe, black holes are long-lived objects. Stellar mass black holes can persist for immense spans of time. Supermassive black holes may outlast generations of stars. If black holes slowly evaporate through quantum effects, the timescales for large ones are far beyond the current age of the universe. They may become especially important in the far future, when star formation fades and the cosmos grows darker. For now, they are both active engines in galaxies and quiet gravitational landmarks, shaping nearby matter and testing our theories. At the centres of many galaxies, supermassive black holes influence their surroundings. Gas falling toward them can release tremendous energy before crossing the horizon, powering active galactic nuclei and quasars. These objects can be seen across great distances, which means we see them as they were in the earlier universe. Some of the brightest distant quasars reveal that enormous black holes already existed when the universe was young. This raises questions about how they grew so quickly, whether from early massive stars, direct collapse of gas, mergers, or other processes. Once again, black holes become clocks of cosmic history. Their masses, growth, and activity tell us something about the timing of galaxy formation. A black hole itself is dark, but the universe around it can be bright with evidence. Stars orbiting the centre of our galaxy reveal the presence of a compact, massive object there. Hot gas around black holes emits radiation. Gravitational waves from merging black holes ripple outward through space and time, carrying information about collisions that happened long ago and far away. These waves are another kind of cosmic signal, not light, but distortions in space itself. They travel across the universe and arrive at detectors on Earth, telling us about events involving extreme gravity. Even the merging of black holes is a timing story, a record of orbits shrinking, horizons joining, and energy leaving as gravitational waves. In all these cases, time is not a passive background. It is shaped, stretched, slowed, and compared. Near black holes, the universe reveals that the rate of time is tied to location in a gravitational field. The deeper the well, the slower the clock relative to far away. The event horizon marks the edge of escape, the point beyond which future paths cannot return outward. For the outside observer, signals from near that edge are increasingly delayed. For the falling observer, the crossing can happen in ordinary local time. The slowest clocks in nature teach us that time is both local and relational. It belongs to paths through gravity. This lesson fits into the larger question we have been following. If time is relative, what time is it for the universe? The answer cannot come from black holes alone, because black holes are local extremes, not the average cosmic flow. But they show why the question must be handled carefully. The universe may have a cosmic age measured by expansion, but inside that universe are places where time runs very differently. A clock near a black hole and a clock drifting in empty intergalactic space do not share time in the simple, everyday sense. Each tells the truth of its own path. The cosmic clock gives the broad rhythm. Gravity wells create local variations, some tiny, some immense. And after looking at these deep wells where time slows almost beyond recognition, it is useful to return to the widest and oldest signal we can observe. Black holes show how gravity can trap light and stretch time near dense masses. The cosmic microwave background shows something almost opposite in scale. Light released when the whole universe became transparent, travelling through expanding space ever since. One is local and extreme. The other is everywhere and ancient. Together they help us understand how clocks can differ from place to place while the universe still carries a shared record of its early state. The next part of the story follows that ancient radiation more closely, because if the cosmos has anything like an old timestamp written across the sky, it is found in that cold background glow arriving from every direction. After thinking about black holes, where gravity can hide light and make distant clocks appear to slow almost to a stop, it is useful to turn toward a very different kind of signal. Not a signal from one object, not a flash from one star, not a message from one galaxy, but a faint glow coming from every direction in the sky. It is older than any star we can see with the naked eye. It is older than the Milky Way in its present form, older than Earth, older than the Sun, older than the first planets, and older than the first heavy elements drifting through space. It is the cosmic microwave background, the cooled leftover radiation from a time when the universe first became transparent. If the universe keeps a record of its early state, this is one of the best pages we're allowed to read. It is not the beginning itself, and that distinction matters, but it is the oldest light that has travelled freely across the cosmos to reach us. It is the universe's earliest visible timestamp, written not in ink, not in stone, and certainly not in the handwriting of anyone trying to remember where they put their glasses, but in tiny differences of temperature spread across the whole sky. To understand why this ancient light exists, we need to return to the universe when it was young, hot, and crowded. Today, space seems mostly empty. Stars are separated by enormous distances, galaxies float in great dark stretches, and even the air around you is dense only by the very generous standards of a human body. The early universe was nothing like that. It was filled with a hot mixture of particles and radiation. It was not a place with stars shining in darkness, because there were not yet stars and there was not yet ordinary darkness in the way we picture it. Matter and light were closely mixed. The temperature was so high that electrons could not settle peacefully around atomic nuclei. Any time an electron and a nucleus tried to form a neutral atom, energetic radiation would knock them apart again. The universe was a bright, dense fog of charged particles, and light could not travel far without being scattered. A photon might begin a journey, bump into a free electron almost immediately, change direction, and then do it again and again. It was less like light crossing an open room, and more like someone trying to walk through a crowded train station, while everyone keeps stepping into the way. This is why the phrase first light has to be handled carefully. The early universe was not dark before the cosmic microwave background was released. In a physical sense, it was full of light, full of radiation, full of energy, but it was opaque. Light existed, yet it could not move freely across large distances. If you had somehow placed an indestructible eye in that universe, which would be a very ambitious and uncomfortable experiment, you would not have seen distant objects because there were no distant objects of the familiar kind, and because the light would not have carried clear images. The universe was more like a glowing fog than a transparent night sky. The change came as space expanded and cooled. Expansion stretched radiation and reduced the average energy of the cosmic contents. After about 380,000 years, the temperature fell enough for electrons to join with nuclei and form neutral atoms, mostly hydrogen and helium. Once that happened, the fog cleared. Photons were no longer constantly scattered by free charged particles. They could finally travel. That release of light is what we observe today as the cosmic microwave background. The photons that began travelling then have been crossing space ever since. While they travelled, the universe continued to expand. Their wavelengths stretched with space. What began as a much hotter glow has cooled into microwave radiation, far too cold and faint for our eyes to see. It now corresponds to a temperature only a little above absolute zero. That number is not just a detail, it is a sign of how much the universe has expanded since the light was released. The ancient glow has been stretched and cooled for billions of years, and its present condition tells us about the scale of cosmic history. Every direction we look, with the right instruments, we see this background radiation. It is behind the stars, behind the galaxies, behind the local clutter of the sky. It is the old light underneath the newer light. The discovery of this radiation is one of the great stories in modern science, partly because it was predicted before it was found, and partly because the actual finding involved a stubborn bit of unwanted noise. In the middle of the 20th century, scientists working on theories of the hot early universe realized that if the universe had once been dense and hot, then leftover radiation from that early state should still exist, cooled by expansion. It should fill space. Later, two researchers using a sensitive radio antenna detected a faint background signal that seemed to come from all directions. They tried to remove possible sources of error. They checked the equipment. They dealt with ordinary practical nuisances, including material left by pigeons, because science is sometimes less glamorous than the textbooks suggest. The signal remained. It was not a local problem. It was not the antenna misbehaving. It was the ancient radiation arriving from the early universe. A quiet hiss in an instrument turned out to be one of the most important messages the cosmos had ever sent us. At first glance, the cosmic microwave background looks almost perfectly uniform. It comes from every direction with nearly the same temperature. This uniformity is astonishing. It tells us that the early universe was extremely smooth, at least when measured on large scales. No stars, no galaxies, no clusters, no vast web of structure yet. Just a hot, nearly even mixture. But the word nearly is doing important work. The cosmic microwave background is not perfectly smooth. It contains tiny variations, small differences in temperature from one patch of sky to another. These differences are extremely slight, but they are the seeds of everything that came later. Slightly denser regions in the early universe had a little more gravitational pull. Over time, they attracted more matter. Those small unevennesses grew into the large structures we observe today. Galaxies, clusters of galaxies, and the enormous cosmic web all trace their ancestry back to tiny patterns in that early light. This is why maps of the cosmic microwave background are so valuable. They are not just pretty images with warm and cool patches. They are records of the universe's early conditions. Scientists study the size and distribution of those patches to learn what the young universe contained and how it behaved. The pattern reveals the influence of ordinary matter, dark matter, radiation, and dark energy. It helps determine the age of the universe. It helps measure the shape of space on the larger scales. It gives clues about the processes that may have happened in the very earliest moments, long before the universe became transparent. The cosmic microwave background is both a photograph and a measurement, both an old glow and a set of data. It is like finding a baby picture that also includes the child's future height, family history, and a surprisingly detailed note about the furniture in the nursery. One of the most important things this ancient light shows us is that the universe was once much simpler in appearance, but not empty of potential. The tiny fluctuations in the background were small enough that the sky looks almost uniform, yet they were large enough to let gravity begin its long work. If the early universe had been perfectly smooth, matter might have remained spread out too evenly for galaxies to form. If it had been much more uneven, structure might have developed too violently. Instead, the universe had small irregularities, and those irregularities grew. Gravity is patient. Given enough time, a slight excess of matter can become a cloud, then a star-forming region, then part of a galaxy. The cosmic microwave background lets us see the starting pattern before gravity had fully turned it into the rich structure of the present-day universe. There is another subtle feature in this old light. The early universe was not silent in the physical sense. Before atoms formed, radiation and matter were coupled together in a hot plasma. Gravity pulled matter inward in slightly denser regions, while radiation pressure pushed back. This created waves moving through the early cosmic material. They were not sound as we hear it in air, because there were no ears, no air, and no cozy room in which to listen. But they were pressure waves, real patterns of compression and rarefaction in the hot plasma. When the universe became transparent, the cosmic microwave background preserved a record of those waves. The sizes of the temperature patches are related to how those early waves had moved by the time light was released. In this way, the background radiation carries the frozen trace of the universe's early vibrations. That trace helps scientists determine the ingredients of the cosmos. Ordinary matter, the kind that makes stars, planets, people, spoons, and inconveniently placed furniture in the dark, affects the pattern in one way. Dark matter, which does not shine or absorb light but has gravity, affects it in another. Radiation leaves its own imprint. Dark energy influences the later expansion and helps connect the early pattern to the universe we see now. When all these effects are compared with detailed observations, a consistent picture emerges. The universe is mostly not made of the ordinary atoms that make us. Ordinary matter is only a fraction of the total cosmic contents. Dark matter and dark energy dominate the large-scale behaviour, even though their deeper nature remains unknown. The cosmic microwave background is one of the strongest pieces of evidence for this strange inventory. This can feel humbling. The oldest light tells us not only that the universe is ancient, but that most of what shapes it is not directly visible. We live in a cosmos where the matter we touch and see is only part of the story. Yet that small visible part matters greatly. Ordinary matter formed stars. Stars made heavier elements. Planets formed from those elements. Biology emerged, at least here. And eventually, ordinary matter arranged itself into instruments capable of measuring the ancient radiation, and minds capable of asking what it means. There is something almost funny about that. A tiny fraction of the universe's contents became aware enough to discover that it was a tiny fraction. The universe has a dry sense of humour. The cosmic microwave background also provides a useful reference frame. Because the radiation fills the sky, our motion through it can be detected. If we move in one direction relative to this background, the radiation appears slightly warmer in the direction of motion, and slightly cooler in the opposite direction. This is similar to the way rain seems to strike more strongly from the front when you run through it, though cosmic radiation is rather more polite and much less likely to ruin your coat. By measuring this pattern, scientists can tell how Earth, the Sun, and the Milky Way are moving relative to the ancient background. Once this motion is accounted for, the radiation appears extremely uniform. That makes the cosmic microwave background a kind of cosmic rest frame, a natural frame for describing the large-scale universe. This does not mean the old absolute time has returned. The background does not create a universal now that every observer must accept in the simple everyday sense. Relativity remains true. Motion and gravity still affect clocks. Different observers can still disagree about simultaneity across great distances. But the cosmic microwave background gives cosmology a physically meaningful way to define a preferred large-scale frame for our universe. It is not preferred because the laws of physics demand it in all possible universes. It is preferred because our universe has this background radiation left over from its hot early state. It is a real feature of the cosmos, and it gives us a useful way to talk about cosmic time. When scientists say the universe is about 13.8 billion years old, the cosmic microwave background is central to that estimate. Its temperature, its patterns, and its relationship to the expansion of space all help fix the timeline. The background was released when the universe was about 380,000 years old. Its light has travelled to us through nearly the entire history of the cosmos. By studying how much it has stretched and what patterns it carries, scientists can infer the age, contents, and evolution of the universe. It is a timestamp, but not a timestamp like a date printed on a photograph. It is a physical condition preserved in radiation. It says that when this light last scattered, the universe had reached a certain temperature, density, and stage of development. From there, the rest of the timeline can be built. The phrase last scattered may sound small, but it is important. The light we see in the cosmic microwave background did not originate from a solid surface like the surface of a star. It comes from everywhere in the early universe, from the moment when photons last interacted strongly with matter before travelling freely. Because we observe this light coming from all directions, It appears to us as if it comes from a distant spherical shell surrounding us. But that shell is not a physical wall. It is the region of the universe from which light, released at that early transparent moment, is reaching us now. An observer in another galaxy would see their own cosmic microwave background sphere, centered on their location. They would be receiving ancient light from different regions. In that sense, everyone has their own view of the oldest visible light, though the underlying early universe was part of one connected cosmic history. This is another reminder that observation is local, even when the signal is universal. The cosmic microwave background fills the universe, but what we see is the portion whose light reaches us today. The light arriving now has been travelling for billions of years. The matter that released it has, in the meantime, evolved into something else. Some of those regions may now be part of galaxies, clusters, or vast stretches far beyond our current direct reach. We are not seeing them as they are in a present-day sense. We are seeing them as they were when the universe was young. The background is therefore not a live image of distant space. It is an old record arriving now. The beauty of that record is its consistency. The same ancient radiation that tells us the universe was once hot also tells us how small early irregularities grew. It connects the smooth beginning with the clumpy present. It explains why the night sky is not just a random scattering of objects, but the result of a long gravitational development. It gives us a way to test ideas about inflation, the possible rapid early expansion that may have stretched tiny fluctuations across cosmic scales. It allows scientists to compare predictions with observations in remarkable detail. Few things in science are as powerful as a signal that comes from nearly every direction and carries information from nearly the beginning of observable time. Still, the cosmic microwave background is not the final word on everything. It cannot show us the very first instant, if the phrase first instant even makes sense under the deepest conditions. It cannot by itself solve the nature of dark matter or dark energy. It does not reveal what happened before the hot dense state, if before is a meaningful word there. It gives a clear image of the universe at a particular early stage and strong clues about earlier and later stages. Like any ancient record, it must be interpreted with care. But the fact that it exists at all is extraordinary. The universe has changed beyond recognition since that light was released, and yet the light remains, stretched and cooled, still readable. There is a quiet contrast between this old background and the bright objects that usually capture our attention. Stars are dramatic, galaxies are beautiful, nebulae look like painted clouds, black holes, though invisible directly, create some of the most extreme environments in nature. The cosmic microwave background is visually modest by comparison. It is faint, cold, and nearly uniform. It does not sparkle. It does not form a familiar shape. It will not appear in the sky like a constellation. But scientifically, it is one of the richest signals we have. It is the old foundation under the visible universe. Without it, our understanding of cosmic time would be far weaker. For the question we have been following, it matters because it helps explain how the universe can have a meaningful age even without a single universal present. The background radiation gives us a shared early reference. It shows a stage through which the observable universe passed. It lets us define cosmic time for observers moving with the expansion. It anchors the story of cooling, expansion, and structure formation. It does not force all clocks everywhere to agree in every situation. A clock near a black hole still differs from a clock in intergalactic space. A fast traveller still measures time differently from someone drifting with the cosmic flow. But the cosmic microwave background gives us a large-scale history against which those local differences can be understood. You can think of it this way. A city may contain many clocks, some accurate, some slow, some fast, some on train stations, some in kitchens, some forgotten in drawers with old batteries. The city also has a history, a founding, a growth, a pattern of streets and buildings that changed over time. The existence of many local clocks does not prevent the city from having an age. In the universe, relativity gives us many local times, while cosmology gives us a large-scale history. The cosmic microwave background is one of the oldest records in that history. It tells us what the city looked like when the foundations were still wet, long before the towers rose. Right now, that ancient radiation is passing through you and through the room around you. It is harmless, faint, and unnoticed by the senses. You do not feel it on your skin. It does not warm your tea. It does not make the curtains move. But it is there, part of the background of reality, arriving from every direction. Each photon has travelled across expanding space since the universe became transparent. Many have crossed regions that later formed galaxies and voids. They have passed through a cosmos changing around them, while their own wavelengths stretched with that change. By the time they arrive here, they are cold relics of a hot beginning. That thought can make an ordinary room feel slightly larger. The local clock may say it is late. Your body may be preparing for sleep. Outside, clouds may cover the stars, or city lights may hide the Milky Way, or morning may already be brightening the edge of the day. None of that stops the ancient background from being present. Beneath all local weather and human schedules, the universe carries this old radiation like a memory. It is not memory in the human sense, not something thinking or remembering, but a physical trace of an earlier condition. The cosmos does not need to recall its past. Its past is written into what still exists. And the timestamp points forward as well as backward. The cosmic microwave background tells us where the universe came from, but it also reminds us that the universe continues to change. As expansion goes on, the background will keep cooling. Its wavelengths will stretch farther. Future observers, if any exist in the very distant future, may find it hard to detect. The sky will change. Star formation will slow. Galaxies beyond our local gravitational neighbourhood may fade from view as expansion carries them beyond reach. The ancient timestamp that is so useful to us may become nearly unreadable to anyone living unimaginably far ahead. We are observing the universe at a time when its oldest light is still available, still measurable, still telling its story clearly enough for patient instruments to hear. That leads naturally into the far future, because a timestamp is not only a mark of when something began, it is also a reminder that time continues. The universe that once released the cosmic microwave background is not the universe that exists now, and the universe that exists now is not the one that will exist after the stars fade and the great structures drift into deeper isolation. If cosmic time is measured by expansion, cooling and change, then the future is not simply more of the present. It is another era, quieter, colder and stranger, where the question of what time it is for the universe may have an answer, measured less by shining stars and more by what remains when most of the familiar lights have gone. The ancient background light reminds us that the universe has already changed beyond recognition once, and it will keep changing long after the present sky is gone. The stars above us feel permanent because they outlive human lives so completely. A person can grow old beneath the same constellations. Civilizations can rise, vanish, and be rediscovered while the stars seem to keep their quiet places. Even the sun, which gives every day its shape, has been shining for billions of years and will continue for billions more. On our scale, stars are the definition of endurance. They are the slow lamps of the cosmos, the steady markers by which sailors, astronomers, calendars, and late-night thinkers have found their bearings. But stars are not eternal. They are temporary fires. Very long temporary fires, yes, the sort of temporary that makes a mountain look like a passing thought, but temporary all the same. This matters for cosmic time because we currently live in a bright era. Not bright everywhere, of course. Space is mostly dark and thin, with galaxies scattered through it like islands. But compared with the far future, the universe we inhabit is lively. Stars are forming. Galaxies still glow. Gas clouds still collapse. Supernovae still seed space with heavy elements. Planets still orbit stable suns. The cosmic microwave background is still measurable. Distant galaxies are still visible across enormous reaches of space. We live in a universe old enough to be complex, but still young enough to be readable. The clocks around us are many. Stellar clocks, planetary clocks, biological clocks, atomic clocks, and the broad cosmic clock of expansion all still have something to say. The far future changes that. If we follow the universe forward, not just millions or billions of years, but far beyond the age it has already reached, the meaning of cosmic time begins to shift. The universe does not end all at once like a theatre curtain dropping after the final line. It fades through eras. First the familiar stars change, then new star formation slows, then galaxies age, then stellar remnants dominate, then black holes become increasingly important. Then, if our current understanding is broadly right, the cosmos becomes colder, darker, emptier, and more isolated. Time still passes locally. Clocks can still tick in principle. But the universe becomes a place with fewer events by which to mark that passage. It is not that time stops. It is that the usual ways of noticing time begin to disappear. The first part of this future is close enough in cosmic terms to be described through the life of the Sun. The Sun is a middle-aged star, steady because hydrogen in its core is being converted into helium. That process cannot last forever. Over billions of years, the Sun will change. It will become brighter, altering conditions on Earth long before it reaches its dramatic later stages. Eventually it will swell into a red giant, shedding outer layers and leaving behind a dense white dwarf. Earth's future in that process is not a cosy one, and it is best not to think of long-term real estate planning on this planet as extending quite that far. But the Sun is only one star among many, and its story is part of a larger stellar pattern. Massive stars live fast. They burn their fuel quickly, shine intensely, and die young by cosmic standards, often ending in supernova explosions and leaving neutron stars or black holes behind. Smaller stars live more slowly. Red dwarfs, the smallest ordinary hydrogen-burning stars, can shine for extremely long times, far longer than the current age of the universe. They burn their fuel gently and efficiently. If the universe has patient lamps, red dwarfs are among the most patient. Long after stars like the Sun have become white dwarfs, many red dwarfs may still glow faintly. In the far future, they will be the last ordinary stars shining. But even red dwarfs have limits. Eventually, the supply of gas for making new stars will run low. Star formation depends on cold gas clouds collapsing under gravity. Over time, gas is locked into stars, blown out by stellar winds, heated, stirred, used and reused. Galaxies can continue forming stars for a long while, especially if they merge with other galaxies and compress their gas. But the general trend is decline. The universe has already passed the peak era of star formation. In the far future, fewer new stars will be born. The galaxies will age. Their bright blue young stars will vanish first, because such stars burn quickly. The remaining light will come from longer-lived smaller stars, then from the fading remnants of stars that once were. This gives cosmic time a different texture. Today, time can be marked by creation as well as decay. New stars ignite, new planets form, new heavy elements are made. The universe is not simply winding down in every local sense. It is still building things. In the far future, building becomes rare. The universe shifts from an era of formation to an era of remnants. White dwarfs, neutron stars, brown dwarfs, and black holes become the main objects left behind. Galaxies become dimmer and redder, filled with old stars and stellar ashes. A night sky in such a future, seen from some surviving world if any such place remains, would look much less rich than ours. The bright star-forming regions would be gone. The dramatic clouds of glowing gas would fade. The universe would not be empty, but it would be quieter. White dwarfs are important in this long fading. A white dwarf is the exposed core left behind by a star like the Sun after it has shed its outer layers. It is hot at first, but it has no ongoing fusion in the usual sense. It shines by stored heat slowly cooling over immense times. Given enough time, white dwarfs will grow colder and dimmer. In a future far beyond the present age of the universe, they may become black dwarfs, cold stellar remnants no longer shining visibly. No black dwarfs exist yet because the universe is not old enough for white dwarfs to have cooled that far. That fact alone is a useful reminder that cosmic time is not only about what has happened, but about what has not had time to happen yet. Some objects are predicted not because we have seen them, but because known processes have not run long enough to produce them. Neutron stars also linger. They are the collapsed cores of massive stars, dense beyond ordinary imagination. Over long times they cool and spin down. Some may remain as dark, dense relics. Black holes too remain, especially because they are difficult things to get rid of. Once formed, a black hole can persist for extraordinary spans of time. It may grow by swallowing matter or merging with other black holes. In the far future, when stars have faded and ordinary matter has become locked in remnants or scattered thinly, black holes may become the dominant large objects in many regions. They will be the last great gravitational landmarks, dark centers in an increasingly dim universe. Meanwhile, expansion continues. If dark energy behaves as current observations suggest, the expansion of the universe will keep accelerating. Distant galaxies not gravitationally bound to our local group will recede beyond reach. Their light will be stretched more and more, becoming fainter and lower in energy. Eventually, future observers in our local gravitational neighborhood may no longer be able to see the wider cosmic web. The universe beyond the local group may vanish from practical view, not because it ceases to exist, but because expansion prevents its light from reaching them in a usable way. The sky would grow emptier. The evidence that once allowed us to infer the Big Bang, cosmic expansion, and the large-scale structure of the universe might become faint or inaccessible. This is one of the stranger consequences of cosmic timing. We live during an era when the universe is observable in a particularly rich way. We can see distant galaxies. We can detect the cosmic microwave background. We can measure expansion. We can compare young galaxies with old ones by looking across distance. But in the far future, an astronomer limited to a merged local galaxy might see mostly local stars and remnants. The cosmic microwave background would be stretched to wavelengths so long and temperatures so low that detecting it could become extremely difficult. Distant galaxies would have disappeared beyond the horizon of observation. The universe would still have the same deeper history, but the evidence would be hidden by time itself. Not destroyed exactly, but stretched away, cooled down, and carried beyond reach. That thought gives a practical meaning to the question of what time it is for the universe. We are living in an era when the universe can still be studied as a whole. The cosmic clock is readable. The oldest light is still present. The galaxy population still reveals different ages and stages. There are enough bright sources to map the expansion. If intelligent observers emerge much later, they may find themselves in a darker and more isolated cosmos, with fewer clues. Their local time may be perfectly clear, but cosmic time may be harder to reconstruct. The universe may have hidden its birth certificate in an attic whose stairs have quietly disappeared. As the stellar era fades, time becomes marked more by rare events. Stellar remnants may occasionally collide. Orbits may be disturbed. Black holes may merge. Old planetary systems may be disrupted by close encounters over enormous spans. Matter may slowly decay if protons are unstable, though this remains uncertain. If proton decay occurs, ordinary matter itself would gradually break down over fantastically long times. If protons do not decay, matter can last far longer, locked in cold remnants and thin dust. The details depend on physics we do not yet fully know. The far future is not a single confirmed script. It is a set of possibilities based on current understanding. Still, most long-term scenarios share a broad direction. Usable energy becomes less available, temperature differences shrink, bright processes become rarer, entropy increases. The universe moves toward a state often described as heat death. Though the phrase can be misleading, it does not mean everything becomes hot. It means the universe approaches a condition in which energy is spread out in a way that makes it difficult to do work. Stars no longer provide steady, fresh energy. Temperature differences that power processes fade. The cosmos becomes cold, thin, and quiet. In such a future, time might continue indefinitely, but fewer and fewer organized changes would occur. This is where the meaning of time begins to feel different. In our lives, time is measured by change. A kettle warms, shadows move, a body grows tired, a child learns to speak, seasons turn, stars rise and set because Earth rotates. Even our thoughts give time texture, one idea after another. In physics, time can be measured by clocks, but a clock itself is a changing system. Something must oscillate, decay, move, vibrate, or count repeated events. If the far future contains fewer active systems, fewer bright engines, fewer strong gradients of energy, then the universe may still have time in a formal sense, but it becomes harder to find clocks that matter in the familiar way. A cold remnant drifting in darkness does not provide much of a diary. Black holes, however, bring their own long clock. According to the combination of general relativity and quantum theory, black holes are expected to emit a faint radiation and lose mass slowly over time. This is known as Hawking radiation. For black holes of ordinary astrophysical size, the process is incredibly slow. The larger the black hole, the colder and longer lived it is. A stellar mass black hole would take an unimaginable span of time to evaporate. A supermassive black hole would last vastly longer. These times are so far beyond the present age of the universe that ordinary language almost gives up and makes tea. But if the process is correct, then even black holes are not eternal. They too become clocks, counting down through a nearly silent leakage of energy. In the farthest future, after stars have gone quiet and matter has thinned or decayed or settled into remnants, black hole evaporation may become one of the last significant processes. The universe might be dominated by black holes slowly losing mass into faint radiation. Eventually, even they would disappear, leaving behind an extremely dilute bath of particles and radiation. The great gravitational wells would smooth away. The last loud clocks would fall silent. What remains would be a universe still described by time, but almost empty of events recognizable to us. It's important not to make this sound more certain than it is. The very far future depends on the nature of dark energy, the stability of matter, the correct theory of quantum gravity, and other questions that remain open. Dark energy could behave differently from a simple constant. It might change over time. Some speculative possibilities imagine a future in which expansion becomes so extreme that bound structures are eventually torn apart, though this is not the standard expectation. Other possibilities involve vacuum decay, where the state of the universe could change in a sudden and dramatic way, but this is highly speculative and not something to lose sleep over, especially during a sleep science journey. The most widely discussed picture remains long cooling, fading, isolation, and increasing entropy. That picture can feel bleak if we imagine it as an ending with no meaning, but it can also be understood simply as scale. The universe does not arrange itself around human preferences for a satisfying finale. Stars form because gravity, gas, pressure, and nuclear physics allow them to. Stars die because fuel is finite. Galaxies evolve because matter moves and interacts. Expansion accelerates because the large-scale contents of the universe drive it that way. The far future is not cruel. It is the continuation of physical processes across time so long that our emotional instincts struggle to follow them. We are creatures of days and decades trying to picture durations beyond stars. There is also a gentler way to look at it. The fact that stars will one day go quiet does not make their shining less real. A candle is not meaningless because it burns down. A song is not empty because it ends. A summer afternoon is not wasted because winter exists. The universe, at this time, is full of stars because earlier conditions allowed stars to form. We live during that luminous interval. The far future gives contrast to the present cosmic era. It tells us that starlight is not the default state of reality forever. It is a phase, a long and magnificent phase, but a phase. That makes the current universe not less important, but more specific. We are not just in the universe, we are in the starlit age of the universe. In that starlit age, time has many visible markers. Stars change colour and brightness as they age. Galaxies collide and merge. Gas clouds form new suns. Planets carry seasons. Biological life, at least on Earth, builds memory and anticipation out of chemical processes. In the far future, many of these markers vanish. If no new stars form, there are no new planetary systems in the ordinary sense. If galaxies beyond the local group disappear from view, cosmic history becomes harder to read. If the background radiation fades beyond practical detection, the oldest timestamp becomes nearly silent. A clock can still tick somewhere, but the universe becomes less generous with clocks. The far future also changes the meaning of distance. Today, when we look far away, we look back in time. Distant galaxies are windows into the younger universe. In a far future dominated by accelerating expansion, most distant galaxies would no longer be visible. The observable universe of future beings would shrink in content, even if space itself remains vast. Their sky might contain the merged remains of the Milky Way and Andromeda, along with other local group members, but the great cosmic web would be gone from sight. Without access to that wider evidence, they might conclude that their galaxy island is all there is. Cosmic truth would still exist, but observation would be poorer. Time would have erased the easy clues. This is not erasure in the sense of destruction. It is more like watching a landscape disappear in fog as you move away, except the fog is expansion, and the movement is built into the geometry of the universe. The distant galaxies are not necessarily destroyed by becoming unobservable. They are placed beyond communication. The universe becomes a collection of isolated regions, each increasingly alone. Time, in that future, is not shared through signals across the vast cosmic distances in the way it can be now. Local histories continue, but the ability to compare them fades. This returns us to relativity in a new way. We began by asking whether the universe has a time. Relativity told us there is no single, simple now for everything. Cosmology gave us a large-scale cosmic time tied to expansion. Black holes showed that local gravity can make clocks differ dramatically. The cosmic microwave background gave us an ancient timestamp that helps define the shared early history. The far future shows that even the ability to read cosmic time depends on the era in which observers exist. A universe may have a history, but not every era offers the same access to that history. For us, the cosmic microwave background is still present. Distant galaxies still glow, stars still burn. The universe is not young, but it is not old in the way it will become. It is middle-aged only by certain measures, and very young compared with the possible lifetime of red dwarfs, black holes, and the long cold future. We live after the first stars and before the last stars, after the first atoms and before the last black holes, after the cosmic fog cleared and before the evidence fades into unreachable cold. The present cosmic time is a window, and science is one way of noticing that the window is open. There is a practical humility in this. When we say the universe is about 13.8 billion years old, we are not just naming a number. We are naming our position in a long sequence of physical eras. We are late enough to look back, early enough to see far, and lucky enough in the plain scientific sense, to inhabit a time when the clues are abundant. The stars have not gone quiet. The background has not faded beyond recognition. expansion has not yet hidden the great galaxy fields from us. The universe still permits its history to be read by beings who learned how to build patient instruments. And perhaps that is the calmest way to think about the far future, not as a reason for sadness, but as a scale that helps define the present. The stars will not shine forever, which means the star-filled universe is an era. The cosmic microwave background will not remain easily detectable forever, which means the ancient light is a present opportunity. Distant galaxies will not remain reachable by observation forever, which means the deep sky is a temporary archive. Time for the universe is not merely the ticking away of years, it is the changing availability of structure, light, energy, and memory. When stars go quiet, time does not need to stop. A quiet universe can still have duration. A cold particle drifting through emptiness still has a path. A black hole slowly evaporating still marks an immense interval. But the universe will have fewer bright ways to announce that time is passing. It will no longer mark itself with new suns, glowing nebulae, active galaxies, and rich skies. Its clocks will be slower, rarer, and more difficult to read. The cosmic rhythm will have stretched into something almost still. That thought brings us back gently to the room, to the local clock, to the ordinary present that relativity taught us not to stretch carelessly across everything. The time on your clock is small and immediate. The time of the universe is vast and layered. Yet the two are connected. Your clock exists in the starlit era. Your body exists because earlier stars lived and died. Your thoughts about the far future occur while the cosmic background still passes through space and galaxies still shine across the dark. The universe has no master clock in the old sense, but it has a history, and for a little while that history is visible. The final step is to gather these ideas without forcing them into a simpler shape than they deserve, and to return to the human question inside the cosmic one. What it means to live inside a universe that has no single clock, no universal now, and yet still gives every local moment its own quiet reality. So here we are, back from the far future, back from the fading stars, back from black holes, ancient light, expanding space, and all the strange clocks the universe allows. It is worth letting the whole journey settle for a moment, not as a grand final answer tied neatly with string, but as a clearer way of holding the question we began with. If time is relative, what time is it for the universe? At first, that question sounds as though it should have a single number for an answer. We're used to questions about time being answered that way. What time is it now? It is late. It is morning. It is 10 past something. It is almost tomorrow. It is far too early for leaf blowers. A clock gives the answer, and the matter is settled. But the universe does not answer like a clock on a kitchen wall. It answers through expansion, gravity, motion, light, temperature, structure, and history. It answers in layers. The first layer is the one we live with every day. Your local time is real. The clock beside you, the rhythm of your breathing, the tiredness in your body, the slow softening of attention as the evening deepens, all of that belongs to your time. Relativity does not make this ordinary time false. It does not mean clocks are illusions or that yesterday is just a matter of opinion. Local time is the most immediate time there is. A clock that travels with you measures the time along your path through reality. Your body follows that path too. Heartbeats, thoughts, digestion, sleep, memory, and aging all belong to your local history. In that sense, your clock is not pretending. It tells the truth for you here, along the route you take through space and time. The second layer is the relativistic one. Other clocks may not agree if they follow different paths. A fast-moving clock can tick differently from one that stays behind. A clock deeper in gravity can tick differently from one farther away. Near Earth, the differences are usually tiny, though still real. Around satellites, they matter enough that modern navigation must account for them. Near neutron stars and black holes, they become dramatic. A clock near a black hole can run much more slowly compared with one far away. From a distant view, matter falling toward an event horizon seems to slow and fade. From its own local point of view, it continues inward in its own time. The lesson is simple in words and difficult in imagination. Time is not one universal flow shared equally by all things. It is measured along paths, and paths can differ. The third layer is the problem of now. In ordinary life, now feels obvious. It is the moment in which you are listening, thinking, resting, perhaps noticing the weight of a blanket or the faint sound of the room. Nearby, people can share that now well enough, but stretch the word across the cosmos and it becomes less reliable. A distant galaxy does not share your present in the same simple way that a chair across the room does. The light from that galaxy may have travelled for millions or billions of years. You see it as it was, not as it would be assigned in some chosen present-day description. Even after correcting for light travel, different observers moving differently can disagree about which distant events are simultaneous. That is not because the observers are careless. It is built into the structure of space and time. There is no single cosmic now that every observer everywhere must accept. This is perhaps the hardest part to absorb, because our minds are so comfortable with the idea of a universal present. We imagine the universe as it is right now all at once, as though reality were a vast room and everything in it could be listed at the same moment. Earth here, Mars there, a star-forming region over there, a black hole at a galactic centre, a distant galaxy in some current condition beyond our view. Relativity does not say the events are unreal. It says the slicing of all those distant events into one present is not unique. The universe has events and relationships. It has signals that can travel, causes that can lead to effects, and histories that can be measured. But it does not come with one master present stamped across every galaxy. Then comes the cosmological layer, which at first seems to bring back something like a universal time, but in a more careful way. The universe, when viewed on very large scales, is remarkably uniform. It has expanded and cooled from a hot, dense early state. Observers moving with that overall expansion can define a shared cosmic time. This is the time used when scientists say the universe is about 13.8 billion years old. That number is not the reading of a clock outside the universe. There is no outside clock room, no cosmic caretaker winding the mechanism. It is the time measured in the standard cosmological frame, the frame of observers carried along with the general expansion of space. It is a natural and useful way to describe the universe's large-scale history. That cosmic time is not a contradiction of relativity. It is an application of relativity to the universe we actually inhabit. The universe contains a real background structure, most importantly the ancient radiation known as the cosmic microwave background. This old light fills the sky, cooled by expansion, arriving from the time when the universe first became transparent. Observers can measure their motion relative to it. Once that motion is accounted for, the background appears almost the same in every direction. This gives cosmology a practical frame for describing expansion and age. It is not absolute time in the old sense. It is not a command that all clocks must obey equally. It is a cosmic measuring system built from the actual contents and history of the universe. The cosmic microwave background is one of the clearest reminders that the universe has a past we can read. It was released when the universe was about 380,000 years old, after expansion had cooled the young cosmos enough for neutral atoms to form and for light to travel freely. That light has crossed space ever since, stretched from a hot early glow into cold microwave radiation. It is not the very first instant. It is not a photograph of creation itself, but it is the oldest freely travelling light we can observe, and it carries information about the early universe with astonishing precision. Tiny variations in its temperature mark the seeds from which galaxies and clusters eventually grew. Its overall temperature tells us how much expansion has stretched it. Its pattern helps reveal the ingredients of the cosmos. In a universe without a master clock, It is one of the closest things we have to an ancient timestamp, so the answer to the question is not just one thing. What time is it for the universe? In the standard cosmological sense, it is about 13.8 billion years after the hot dense early state. It is the era after the first atoms, after the first stars, after the first galaxies, after many generations of stellar birth and death. It is the era in which dark energy appears to be accelerating the expansion of space. It is the era when galaxies still shine, stars still form, planets still exist, and the oldest light is still detectable. It is not early in the simple sense, because much has already happened. It is not late in the ultimate sense, because the future may stretch far beyond the current age. It is a starlit middle period, rich with evidence, active with structure, and still bright enough for the universe to be studied from within. That phrase "from within" matters. We do not observe the universe from a balcony outside space and time. We cannot step away from the cosmos and check its wristwatch. We are inside the system we study. Our clocks, telescopes, bodies, and thoughts are all part of the universe. The atoms in our instruments were made by cosmic history. The elements in our bodies were forged in stars and stellar explosions. The light entering our telescopes travelled through expanding space. The mathematics we use is carried out by brains made of matter that the universe assembled over billions of years. When we ask what time it is for the universe, the question is being asked by a small piece of the universe that learned how to build clocks. This does not make the science less trustworthy. It makes it more remarkable. From one planet around one ordinary star, we can infer the age of the cosmos, the existence of ancient radiation, the expansion of space, the presence of dark matter and dark energy, the life cycles of stars, and the time-slowing effects of gravity. We do this not by standing outside reality, but by comparing signals inside it. We read light, motion, patterns, temperatures, and clock differences. We accept that distant observations are also observations of the past. We correct for motion and gravity. We build models that must agree with what the universe actually shows. Science is not a view from nowhere. It is careful seeing from somewhere. There is a useful humility in that. The universe does not owe us an answer shaped like common sense. Our common sense was built for a world of slow speeds, weak gravity, nearby objects, and short lifetimes. It helps us catch cups before they fall, cross roads without disaster, and decide whether a soup is too hot. It was not built to picture a black hole horizon, a galaxy 10 billion light-years away, or the relativity of simultaneity across cosmic distances. So when the universe tells us that time is local, that now is not universal, and that the cosmic age is defined through expansion rather than a master clock, we should not be surprised that it feels strange. It should feel strange. We're asking a human brain to follow a non-human scale. Still, the strangeness does not remove the comfort of the local present. In fact, it may make it more precious in a plain and practical way. Your now is not the whole universe's now, because there is no such thing in the simple absolute sense. But your now is still real. It is the part of space-time you occupy. It is where your life happens. It is where decisions are made, where rest arrives, where attention settles, where curiosity opens and closes like a quiet hand. The lack of a cosmic master clock does not make the present meaningless. It makes the present local, and local things can matter deeply. A home is local, a voice is local, a heartbeat is local, sleep is local, kindness is local. None of these need to stretch across the universe to be real. The far future adds another kind of clarity. Stars will not shine forever. The bright era of the universe is temporary, though temporary on a scale so long that the word almost becomes funny. Star formation will fade. Red dwarfs will be the last ordinary stars. White dwarfs will cool. Black holes may dominate and then slowly evaporate across immense spans of time. Distant galaxies may slip beyond observation as expansion accelerates. The cosmic microwave background will keep stretching and cooling until it becomes harder and harder to detect. Future observers, if any exist, may not have access to the same evidence we do. They may live in a darker, more isolated universe, with fewer clues to the grand history that produced them. This means our cosmic era has a special usefulness. Not special because the universe arranged itself for us, but special because the evidence is still available. We can see galaxies at many stages of development. We can detect the ancient background glow. We can measure expansion. We can observe stars being born and stars dying. We can study black holes, gravitational waves, elemental abundances, and the large-scale cosmic web. The universe is old enough to contain observers and young enough to reveal its past. It is a good time, scientifically speaking, to ask what time it is. There is a gentle irony in that. The universe has no master clock, but it has given us many clocks. Atomic transitions tick with astonishing precision. Pulsars spin like celestial lighthouses. White dwarfs cool. Stars evolve. Galaxies age. Light stretches with expansion. The cosmic microwave background cools. Black holes bend time near their horizons. Biological life tracks days through circadian rhythms. Human memory turns events into a personal timeline. None of these clocks is the one clock. Each measures time in its own way, under its own conditions. Together, they give a richer answer than any single clock could. And perhaps that is the best way to live with the question. The universe does not have a master clock, but it has order. It does not have one universal now, but it has causal structure. It does not give every observer the same elapsed time, but each clock tells the truth of its own path. It does not present its history all at once, but it sends light across space, carrying records from earlier times. It does not stay the same, but its changes are understandable. Time in the universe is not simple, but it is not meaningless. It is woven into motion, gravity, expansion, and change. So when someone asks what time it is for the universe, we can answer carefully. It is locally different for different clocks. It is not governed by a single cosmic present. In the broad cosmological frame, the universe is about 13.8 billion years old. In terms of its condition, it is in a starlit era, long after the first light was released, long after the first structures formed, but long before the last stars fade. It is old enough for the ingredients of life to exist, old enough for galaxies to mature, old enough for the ancient background to be cold and faint. It is still young enough for the sky to be full of evidence. That is not one answer replacing all others. It is the layered answer the universe allows. Now, let the scale come back down. There may be no master clock for the cosmos, but there may be a clock near you. It may be glowing on a phone, sitting on a wall, or quietly existing somewhere you have not checked in a while because checking it might be too much information. It tells you the local time. Maybe it is late. Maybe it is very late. Maybe you're listening from a city where the streets are quiet, or a countryside where the dark is deep, or a room where the day has finally stopped asking things of you. Wherever you are, your time is yours. It is part of the universe's time, but not swallowed by the universe's scale. The same reality that contains black holes and ancient radiation also contains this small present moment. That is one of the calmest conclusions physics can offer. We are not outside the universe, and we are not central to it in the old dramatic sense, but we are inside it, made by it, able to measure it, and able to wonder about it. Our clocks are local, but they are not disconnected. They run in a cosmos shaped by expansion and gravity. Our bodies age according to their path through spacetime. Our atoms carry the history of stars. Our telescopes receive light that has travelled longer than Earth has existed. Every ordinary second is small, and yet it belongs to a universe with a deep past and an enormous future. So if time feels slippery, that is because it is. If now feels both obvious and impossible to stretch across the universe, that is because both are true. If the age of the universe sounds precise and yet rests on a careful choice of cosmic frame, that is not a weakness. It is the honest shape of modern physics. Time is not the same everywhere, and still the universe has a history. There is no single master clock, and still we can count. There is no cosmic now, and still this moment is real. As this quiet journey comes to rest, let me ask again what we asked near the beginning. What time is it where you are? And where are you listening from tonight, in your own little region of space-time? Perhaps the answer is written on a clock. Perhaps it is written in the heaviness of your eyelids. Perhaps it is written in the simple fact that you have followed the thought this far. From bedside time to cosmic time, from Einstein's clocks to the oldest light, from expanding space to the long future after stars go quiet. If you found the journey calming, or if it gave your thoughts a peaceful place to wander, I would be grateful if you liked the video, subscribed, or shared this gentle corner of physics with someone else who might enjoy drifting through big questions at a slower pace. The universe does not tick in one voice. It has no master clock above the galaxies, no single now crossing every star, no grand timekeeper tapping a finger and keeping everyone in line. Instead, it has countless clocks, each following its own path, and one vast history written in light, matter, gravity, and expansion. And here, for a short while, in this local now, we get to notice. Sleep well, fellow traveller, wherever you are, whatever your clock says, and whatever time it happens to be in the small, real, quiet universe around you.